Hello there, and welcome to Physics with William, where curiosity gets cosy and science takes the scenic route to slumber. Tonight, we're going to drift toward one of the quietest but most important questions in modern physics. Are there particles beyond the standard model? It sounds at first like a question meant for a laboratory filled with magnets, cables, glowing screens, and people who drink coffee from mugs covered in particle diagrams. And yes, it certainly belongs there. But it also belongs here, in this slower place, where we can let the question breathe a little. Because beneath all the mathematics and machines, beneath the names that sound like tiny creatures from a very serious fairy tale, quarks, leptons, bosons, neutrinos, gluons, there is a simple human wonder. Have we found all the basic pieces of nature, or is the universe still keeping a few small cards hidden up its sleeve? That is a strange thought, is it not? We look out at the night sky and see stars, planets, clouds of gas, distant galaxies, and the soft blackness between them. Everything seems enormous. Everything seems far too large for the mind to hold at once. But the deeper story may depend on things so small that no eye can ever see them directly. The chair beneath you, the air in the room, the warm mug beside the bed, the hand that reaches for it, the atoms in that hand, and the smaller ingredients inside those atoms, all of it seems to be built from a short list of known particles. A surprisingly neat list, at least at first glance. Physics has spent more than a century trying to discover that list, test it, challenge it, and ask whether it is complete. And the answer, rather wonderfully and rather inconveniently, appears to be no, probably not. Before we go any farther, let me ask you something gently as we settle into this little journey together. Where are you listening from tonight, and what time is it in your corner of the world? Perhaps it is late evening, and the room has gone quiet except for a soft fan, a distant car, or the faint creak of a house cooling down. Perhaps it is morning, and you have this playing in the background while the day is only just beginning to assemble itself. Maybe you're somewhere between sleep and thought, letting the words come and go without needing to hold every detail. However you arrived here, I'm glad you did, because tonight we're not going to race through the universe. We're going to take the slow path, the patient path, the one that lets even the smallest particles feel spacious. And if you find this kind of journey soothing, if you enjoy having science explained gently enough to rest with, or if this little corner of calm helps you unwind after a long day, I would be very grateful if you gave the video a like and subscribed. It helps Physics with William reach other curious minds who might also want to fall asleep beside a black hole, a quantum field, or in this case, a possible particle that nobody has ever seen. I do hope the mystery does not keep you too awake, but if it does, at least you will have spent the time with some of the deepest questions human beings have ever asked, which is not the worst way to lose a little sleep. So, settle in. Let your shoulders loosen. Let the day slowly step back from the edge of your thoughts. Tonight, we're going to begin with the familiar world of matter and then move, carefully and quietly, toward the edge of what we know. Because the standard model is not just a theory in a textbook. It is one of the most successful maps of reality ever made. It describes the particles that make up ordinary matter and the forces that tell those particles how to behave. It explains why atoms hold together, why light interacts with charged things, why certain particles decay, and why the sun can shine. It has predicted discoveries before they were made. It has survived tests of astonishing precision. It is in many ways a masterpiece. And yet, like many masterpieces, it has something missing. Not a careless gap exactly, more like a locked door at the end of a very elegant hallway. The standard model works beautifully for what it was built to explain, but the universe seems larger than the model allows. It does not explain dark matter, even though dark matter appears to shape galaxies and bend the motion of stars. It does not explain why neutrinos have tiny masses, when the simplest version of the model expected them not to. It does not include gravity in the same clean particle language as the other forces. It does not tell us why matter survived the early universe, instead of being completely cancelled out by antimatter. And it does not tell us why the known particles have the particular masses and patterns that they do. It gives us the rules, but not always the reasons behind the rules. Imagine finding a beautifully written instruction manual for a machine in your attic. The manual is precise. It tells you which gears move, which wires connect, which switches start the motor, and which lights come on when the whole thing works. You test it, and again the manual is right. But then you notice something odd. The machine is doing a few things the manual never mentions. A soft vibration under the floorboards, a hidden heat source, a little hum behind a panel that appears to have no screws. You would not throw the manual away. It is clearly useful. It is clearly brilliant. But you would begin to suspect that the machine has another layer, something behind the visible parts. That is roughly where particle physics finds itself. The known particles are not like tiny marbles in the ordinary sense. That is often the picture we begin with because it is simple and friendly. Tiny balls bumping into other tiny balls, a nice image, very comforting, also mostly wrong. In modern physics, particles are more like ripples or excitations in underlying fields that fill space. An electron is not a tiny bead sitting in emptiness. It is a certain kind of disturbance in the electron field. A photon is a disturbance in the electromagnetic field. A quark is a disturbance in a quark field. The universe, seen this way, is less like a box of little objects and more like a set of invisible oceans, each capable of making its own kind of wave. Most of the time, those waves behave so consistently that we call them particles, which is fair enough. If a wave keeps showing up in your detector like a particle, leaves tracks like a particle, transfers energy like a particle, and gives experimental physicists sleepless nights like a particle, then calling it a particle seems reasonable. But once you see particles as signs of fields, the question becomes even more interesting. Are there fields we have not found yet? Are there ripples in nature that pass through us unnoticed because they barely interact with ordinary matter? Could there be particles that are all around us, moving through Earth, through walls, through our bodies, and through the quiet space between sentences, without leaving a mark strong enough for our instruments to catch? This may sound like imagination, but it is not careless imagination. It is the kind of disciplined wondering that physics is built on. Every known particle was once unknown. Every familiar piece of the standard model once lived on the far side of evidence. The electron had to be discovered. The neutrino had to be proposed before it could be detected. The Higgs boson waited in theory for decades before experiments finally found it. Nature has a habit of making us work for the small things. There is also something humbling about the phrase beyond the standard model. It does not mean that the standard model has failed in the ordinary sense. It means that success itself has sharpened the mystery. The more accurately a theory works, the more carefully we can see where it stops. It is like using a very clean window. If the glass is dusty, you might not notice the faint shape beyond it. But when the glass is polished, even the smallest shadow becomes important. Modern particle physics has polished the window to a remarkable degree, and through it, we can see hints that the room may not end where we thought it did. Some of these hints come from the sky. Galaxies rotate in a way that suggests there is more matter than the stars and gas we can see. Clusters of galaxies bend light as if they contain vast amounts of unseen mass. The early universe left patterns that also point towards something invisible, something gravitationally present but not glowing, not absorbing light, not behaving like ordinary atoms. We call it dark matter, which is a wonderfully honest name. It is dark because it does not shine, and matter because gravity seems to say it is there. Beyond that, the name admits that we do not yet know what it is. Dark matter might be made of particles beyond the standard model, or it might force us to rethink gravity on large scales. But in many serious possibilities, there is a new particle hiding in the dark. Other hints come from neutrinos, those famously shy particles that stream from the sun, from exploding stars, from nuclear reactions, and from the early universe itself. Neutrinos are so reluctant to interact that trillions of them can pass through you every second without asking permission, or even politely signing the guestbook. For a long time, they were thought to be massless. But experiments show that neutrinos can change from one type to another as they travel, and that strange changing behaviour means they must have mass, however tiny. The standard model can be adjusted to include this, but the deeper reason remains open. Some physicists wonder whether there are even more hidden neutrino-like particles, sometimes called sterile neutrinos, that interact even less than the ones we know. A particle that makes ordinary neutrinos look sociable is, you must admit, impressively committed to privacy. Then there are ideas that come from the structure of the theory itself. The standard model contains patterns that feel suggestive. There are families of particles, repeated in heavier versions. There are forces that behave very differently at everyday energies, but might once have been more unified in the extreme heat of the early universe. There is the Higgs field, which gives many particles their mass, yet also raises questions about why its own properties are so delicately balanced. Physicists look at these patterns and ask whether something deeper might explain them. Perhaps every known particle has a heavier partner. Perhaps there are particles connected to hidden forces. Perhaps there are fields that solve problems we did not even know how to ask properly until the mathematics pointed toward them. This is where names like supersymmetry, axions, dark photons, and gravitons begin to appear. Some sound elegant, some sound mysterious, some sound like they should have tiny capes, but each represents a serious attempt to understand whether the known particle world is only the visible surface of a larger arrangement. The search itself is also part of the story. How do you look for something when you do not know exactly what it is? That is the difficult art of modern physics. Sometimes you build enormous machines that smash particles together at high energies, hoping that for a tiny fraction of a second, conditions will become intense enough to create something new. Sometimes you build quiet detectors deep underground, shielded from the noise of cosmic rays, waiting for a dark matter particle to bump softly into an atom. Sometimes you watch the sky, studying cosmic rays, supernovae, galaxy clusters, and the leftover light from the early universe. Sometimes you measure known particles with absurd precision, searching for the smallest mismatch between theory and experiment. New physics may announce itself with a dramatic discovery, but it may also arrive as a tiny deviation, a decimal place that refuses to behave, a whisper in the numbers saying, "Look closer." There is something almost funny about the scale of it. To find the smallest things, humans build some of the largest scientific instruments on Earth. We carve tunnels through rock, cool detectors to temperatures colder than deep space, suspend mirrors with extraordinary care, lower tanks of liquid into mines, and sift through rivers of data so vast that no person could read them line by line. We do all this because the universe has left clues, and we are the strange species that decided clues should be followed. A fox hears something under snow and tilts its head. A child finds a shell and wonders where the sea went. A physicist sees an unexplained signal and starts losing sleep in a very professional way. Different scales, same instinct, but we should be careful too. Not every hint becomes a discovery. Physics is full of almosts, almost signals, almost anomalies, almost patterns that fade when more data arrives. This is not failure. It is the process working as it should. Nature is subtle, and human instruments are imperfect. The road beyond the standard model is not a straight march from guess to triumph. It is a long, careful walk through uncertainty. Claims must be tested, results must be repeated, background noise must be understood. A possible new particle must survive the full weight of skepticism. In science, the universe is allowed to be surprising, but it is not allowed to be vague. That is part of what makes this topic so satisfying for a quiet evening. It asks us to hold two thoughts at once. On one hand, we know an extraordinary amount. We have mapped the particle world with a precision that would have astonished earlier generations. We can describe processes inside atoms, inside stars, and inside particle accelerators with deep confidence. On the other hand, we remain surrounded by mysteries. Most of the matter in the universe may be made of something we have not identified. The origin of particle masses is only partly understood. The imbalance between matter and antimatter remains unexplained. Gravity still sits outside the standard model like an old relative at a family gathering, clearly important, deeply connected, but refusing to join the group photograph properly. So tonight, as we begin, we are standing at the border between the known and the possible. Behind us is the standard model, tested, powerful, elegant in its own slightly crowded way. Ahead of us is the question of what might come next, not fantasy, not loose speculation for its own sake, but the careful kind of unknown that science earns after doing something very difficult very well. The unknown that remains after thousands of experiments, decades of theory, and countless people asking again and again, what is the universe made of? And perhaps that is the best way to enter this story, not by imagining that the standard model is broken, but by seeing it as incomplete in the way a coastline map is incomplete when the ocean begins. The land is real, the map is useful, the details are hard won. But beyond the last marked rock, there is still water moving in the dark. Somewhere out there may be particles that shaped the early universe, particles that pass through us unnoticed, particles that explain why galaxies hold together, particles that connect matter to forces we have not yet named. Or perhaps the answer will be stranger still, and the next layer of reality will not look like our expectations at all. For now, we begin with what we know, the familiar particle family, the tiny rulebook that works almost too well, the neat list of ingredients that builds atoms, light, stars, chemistry, and you. Because before we can ask what lies beyond the standard model, we need to understand what the standard model actually says, why it became so successful, and why even its success leaves physicists quietly listening for footsteps behind the wall. To understand why physicists suspect there may be particles beyond the standard model, we first need to spend a little time with the standard model itself, not too quickly, and not as if we are rushing through a museum because someone has already found the gift shop. We should take it slowly, because this theory is not just a list of particles with difficult names. It is one of the most carefully tested descriptions of nature that human beings have ever made. It is a kind of tiny rulebook for the universe, a guide to the ingredients of matter and the forces that act between them. If atoms are the letters of the ordinary world, then the standard model is closer to the alphabet beneath the alphabet, the deeper set of marks from which almost everything around us is written. At first, the idea that the universe has a tiny rulebook may sound a little too neat. The world does not always feel neat. It feels full of weather, laundry, traffic, birthdays, broken mugs, clouds, cats, old stars, and the mysterious ability of charging cables to disappear exactly when needed. Yet underneath that busy surface, physics finds a surprising order. Matter is not made from an endless variety of basic stuff. As far as we can tell, ordinary matter is built from a small family of fundamental particles. These particles do not seem to be made of smaller pieces, at least not according to our best experiments so far. They are the smallest known actors in the physical story, and the standard model tells us who they are, how they behave, and which forces they listen to. The first thing to know is that the standard model divides particles into a few broad families. There are particles of matter, and there are particles associated with forces. The matter particles include quarks and leptons. Quarks are the ingredients inside protons and neutrons. Leptons include the electron, which is probably the most familiar fundamental particle of all, even if we rarely greet it by name when turning on a lamp. Electrons help build atoms. They shape chemistry. They are involved in electricity, magnetism, light emission, and the complicated business of making your phone screen glow when you really should be sleeping. Without electrons, the world would not simply be different. the world as we know it would not hold together in any recognizable way. Quarks are a little less familiar, partly because they are never found wandering alone in ordinary conditions. They are shy in a very strict physical sense. They bind together inside larger particles such as protons and neutrons, held by the strong nuclear force. Protons and neutrons then gather in atomic nuclei, and electrons settle around them, and from that arrangement we get atoms. Atoms join into molecules. Molecules form rocks, oceans, cells, books, blankets, and biscuits. So when someone says the Standard Model explains ordinary matter, this is what they mean. It reaches down beneath atoms, beneath the older picture of protons and neutrons as basic building blocks, and reveals a deeper layer where quarks and electrons do much of the foundational work. There are several kinds of quarks, and several kinds of leptons. Physicists often arrange them into generations, which is a polite way of saying that nature seems to repeat itself with heavier versions of similar particles. The first generation contains the particles that build the stable matter around us. The heavier generations are stranger. They appear in high-energy events, in particle accelerators, in cosmic rays, and in certain particle decays. But they do not form the everyday furniture of the universe. They are like extra cast members who appear briefly in flashbacks or dramatic scenes, then leave before the main story of ordinary matter continues. Why nature has these repeated generations is one of the questions the Standard Model describes but does not deeply explain. It tells us that the pattern is there. It does not fully tell us why the pattern had to be that way. This is one of the first hints that the Standard Model, despite its brilliance, may not be the final story. It is very good at saying what happens. It is less satisfying at explaining why the ingredients have the particular arrangement they do. Imagine being given a recipe that works perfectly every time. The cake rises, the texture is lovely, nobody complains, except perhaps one uncle who believes all desserts should contain raisins. But the recipe never explains why these ingredients were chosen instead of others, or why the quantities are so oddly specific. You would trust the recipe, certainly. But you might still wonder whether there is a deeper culinary principle behind it. Particle physicists are doing something similar, only with less flour and more vacuum chambers. Now, alongside the matter particles, the Standard Model also describes forces. Forces are how particles influence one another. In the everyday world, we talk about pushing, pulling, lifting, falling, sticking, shining, heating, and breaking. Beneath those familiar actions are fundamental interactions. The Standard Model includes three of them: the electromagnetic force, the strong nuclear force, and the weak nuclear force. Gravity, rather importantly, is not included in the Standard Model in the same way, and we will return to that absence later, because it is one of the big unfinished doors in physics. The electromagnetic force is the force of light, electricity, magnetism, and charged particles. It is what allows electrons to interact with atomic nuclei. It is what gives structure to atoms and molecules. It is why solid objects feel solid, even though atoms are mostly empty space in the usual picture. When you place your hand on a table, the particles in your hand are not truly touching the particles in the table, like little hard pebbles pressed together. Instead, electromagnetic interactions resist the overlap. The table pushes back, and you are spared the inconvenience of falling through breakfast. Very kind of it, really. The strong nuclear force is less familiar in daily life, but it is essential. It binds quarks together inside protons and neutrons, and it helps hold atomic nuclei together. This is no small achievement. Protons have positive electric charge, and because like charges repel, they would prefer not to be packed together in a tiny nucleus. The strong force overcomes that repulsion at extremely small distances. It is powerful, but very short-ranged. It works like a firm handshake that only happens if particles are almost on top of one another. Step too far away, and its influence drops from the ordinary scene. Without the strong force, atomic nuclei could not exist as they do. Without nuclei, there would be no atoms heavier than the simplest kind. Without those atoms, no planets, no oceans, no carbon chemistry, no late-night science narration. The strong force is not often thanked in public, but it has done a great deal for us. Then there is the weak nuclear force. The weak force is responsible for certain kinds of particle change. It allows some particles to transform into others, which makes it central to radioactive decay and to the processes that help power stars. It is called weak because, compared with the strong and electromagnetic forces at familiar particle scales, its effects are more subtle. But weak does not mean unimportant. A whisper can still change a room if it says the right thing. The weak force is deeply involved in the sun shining, in nuclear reactions, and in the strange behavior of neutrinos. It is also one of the places where the Standard Model reveals its elegant but complicated machinery. In the Standard Model, forces are not imagined as invisible hands reaching across empty space in the old-fashioned sense. Instead, interactions are described through force-carrying particles. The electromagnetic force is associated with the photon, the strong force is associated with gluons, the weak force is associated with heavy particles that mediate weak interactions. These force carriers are part of the particle family too. They are not matter particles like electrons and quarks, but they are just as real in the theory, and their effects are measured with extraordinary precision. A photon can travel from a lamp to your eye. A gluon can bind quarks together so tightly that trying to pull one quark away creates more particle activity, rather than freeing it like a bead from a string. Nature, at this level, is not always interested in making our simple pictures easy. To make this stranger and more accurate, the Standard Model is really a theory of fields. Each particle corresponds to a field that fills space. The electron field is everywhere. The quark fields are everywhere. The photon field is everywhere. A particle is what happens when one of these fields is excited in a particular way. It is a ripple, a disturbance, a small local expression of something spread throughout the universe. This picture can feel odd at first, because we are used to thinking of objects as things sitting in places. A cup is on the table, a book is on the shelf, a sock is under the bed, probably forever. But a fundamental particle is not quite an object in that everyday sense. It is more like a note played by an invisible instrument that extends through all of space. This field picture is one reason the Standard Model is so powerful. It does not simply catalogue particles. It describes how the fields interact, how particles can be created and destroyed, how one particle can scatter from another, how forces arise, and how probabilities can be calculated. It can predict what should happen when particles collide at high energies. It can predict rare decays. It can explain why some processes happen often and others almost never happen at all. It is not a bedtime story in its mathematical form, unless your idea of a restful evening involves pages of symbols and a very patient lamp. But underneath the technical language is a remarkable idea. The universe has rules at the smallest scales, and those rules are consistent enough for us to test them. Perhaps the most famous piece of the Standard Model story in recent memory is the Higgs boson. For decades, physicists suspected there was a field that gives many particles their mass. Not all mass in the universe comes from this field, and the full story of mass is more layered than the popular version often suggests. But the Higgs field is essential to the Standard Model. Without it, many particles would not have the masses we observe, and the structure of the theory would not match reality. The Higgs boson is the particle associated with excitation of the Higgs field. It was predicted long before it was found, and its discovery was a major triumph for particle physics. It was like hearing a quiet instrument that the orchestra score had insisted must be there, even though nobody had previously managed to pick it out from the noise. That discovery mattered because it showed how bold and accurate the Standard Model could be. Physicists did not simply stumble upon the Higgs boson in a drawer. They built a theoretical structure that required something like it. Then experimental physicists designed enormous machines and detectors capable of searching through countless particle collisions for signs of its presence. The result was not a single photograph of a tiny ball labelled Higgs, smiling politely for the camera. Particle discoveries do not work like that. Instead, physicists found patterns in the debris of collisions, patterns that matched the expected signature of the Higgs boson. It was evidence gathered statistically, patiently, carefully. The universe did not hand over the answer. It allowed itself to be persuaded into revealing it. This is how much of particle physics works. You do not see the particle directly. You see what it leaves behind: tracks, energies, decay products, missing momentum, tiny imbalances. A particle can exist for an almost unimaginably short time and still be known through its consequences. It is a bit like knowing a mouse has been in the kitchen because the cheese has changed shape and there are suspicious crumbs near the skirting board. Only in particle physics the mouse may have existed for less than a blink within a blink, and the cheese is a pattern of detector signals analysed by teams of scientists across the world. Still, the principle is not entirely different. Something happened. The traces remain. From those traces, the hidden actor is inferred. The standard model has been tested again and again in this way. It has survived collisions, decay studies, precision measurements, and comparisons with experiment at levels of accuracy that are genuinely astonishing. In some cases, theoretical predictions and experimental results match so closely that it feels almost unreasonable. The theory is not just broadly correct, it is sharply, stubbornly, impressively correct across a huge range of phenomena. This is why physicists do not casually discard it. Any new theory that goes beyond the standard model must also explain why the standard model works so well. It cannot simply replace it with something unrelated. It must include its success, the way Einstein's theory of gravity had to explain why Newton's older theory worked so beautifully in everyday conditions. A deeper theory does not erase the old map. It shows why the old map was useful and where its borders lie, and those borders are important. The standard model includes the electromagnetic weak and strong interactions, but it does not include gravity as a quantum force. Gravity is described extremely well by general relativity, which treats it as the curvature of space and time. The standard model, meanwhile, lives in the language of quantum fields. Both theories are successful in their own territories, but bringing them together remains difficult. At the scale of planets, stars and galaxies, gravity dominates. At the scale of particles, gravity is usually so weak that it can be ignored. But in extreme places, such as the earliest moments of the universe or the deep interior questions of black holes, both quantum effects and gravity may matter at once. There, our two great descriptions do not yet form one complete picture. It is a little like having two excellent clocks that agree in most rooms of the house, but start arguing near the attic door. The standard model also does not explain dark matter. This is not a small omission. Observations of galaxies and the large-scale structure of the cosmos suggest that the matter we can see, the matter made of atoms and light-emitting material, is only part of the total matter content of the universe. Something else appears to be there gravitationally. It does not shine. It does not absorb or emit light in the usual ways. It does not fit comfortably into the standard model particle list. If dark matter is made of particles, then those particles are beyond the standard model. That does not mean they are magical or impossible. It means our current tiny rulebook does not include them yet. Somewhere, perhaps, there is an extra page. There is also the issue of neutrino mass. Neutrinos are included in the standard model, but their discovered behaviour showed that the original simple version of the model was incomplete. Neutrinos can change identity as they travel, which implies they have mass. Those masses are extremely small, but their existence matters. In physics, small does not mean unimportant. A tiny crack in a wall may tell you the whole building is settling. Neutrino mass suggests that something deeper may be going on, perhaps involving new particles or new mechanisms. The neutrino, already famous for barely interacting with anything, may be quietly pointing toward physics outside the known structure. It is the kind of guest who says almost nothing all evening, then casually mentions a secret passage behind the fireplace. Another puzzle is why the universe is made mostly of matter rather than equal amounts of matter and antimatter. The Standard Model includes antimatter. For every known matter particle, there is an antimatter counterpart with related properties. In the early universe, matter and antimatter should have been created in enormous amounts. When they meet, they can annihilate into energy. So why did matter win even by a small amount, leaving behind the universe we see? The Standard Model contains some ingredients that distinguish matter from antimatter, but not enough, as far as we know, to explain the observed imbalance. This is not merely an accounting issue. If matter had not slightly outnumbered antimatter, there would be no stars, no planets, no chemistry, and no one lying in bed wondering whether particles beyond the Standard Model exist. The fact that anything remained is itself a clue. Then there is the pattern of particle masses. The Standard Model contains values that must be measured and inserted. It tells us how particles behave once those values are known, but it does not fully explain why the electron has its particular mass, why quarks have theirs, why the generations are arranged as they are, or why the Higgs field has the properties it does. This is not a flaw in the sense of making the theory useless. Far from it. But it leaves physicists with the feeling that something remains unexplained. A list of facts can be correct and still not be satisfying. If someone tells you every item in a locked room but refuses to explain why those items are there, you may appreciate the inventory while still wanting the key. This is where the phrase tiny rulebook becomes both helpful and limited. The Standard Model is indeed a rulebook, but it may not be the whole library. It tells us how the known particles interact. It does not tell us why this exact set of particles exists. It does not tell us whether there are hidden sectors of particles that interact only faintly with ours. It does not tell us whether the forces we see today were once unified in a simpler state. It does not explain the full cosmic story from the earliest moments to the dark matter halos around galaxies. It is a brilliant structure with open windows, and through those windows come drafts from colder, stranger rooms. Still, we should not let the mysteries make us forget the achievement. The Standard Model explains an enormous amount of the physical world. The chemistry of life depends on electrons and electromagnetic interactions. The stability of atomic nuclei depends on the strong force. The processes inside stars involve particle interactions described by the theory. The technology around us, from electronics to medical imaging to radiation detectors, rests in part on understanding particles and fields. Even when we're not thinking about it, the Standard Model is there in the background, quietly doing its work. It is in the screen, the lamp, the atoms of the blanket, the calcium in bone, the carbon in cells, and the photons entering the eye. It is not remote from life. It is underneath life, patiently holding the stage. A gentle way to picture it is this. The Standard Model is like a small orchestra playing beneath reality. The electron has its part, the quarks have theirs, the photons carry one kind of melody, gluons hold certain notes tightly together, the weak force changes themes in subtle ways, the Higgs field gives weight to parts of the music. Most of the time, the orchestra plays so smoothly that we do not hear the individual instruments. We hear the world. We hear footsteps, rain, voices, wind in trees, the hum of a refrigerator that somehow becomes much louder at night. Physics is the act of listening carefully enough to notice that the music has parts. And once we listen that carefully, we begin to notice the silences too. The missing bass note of dark matter, the faint off rhythm of neutrinos, the absent instrument of quantum gravity, the strange repetition of particle generations, the unexplained tuning of masses. These silences do not ruin the music. They make us lean closer. They suggest that the orchestra may be larger than the visible stage, with some musicians hidden behind a curtain, playing notes we can feel only indirectly. That is why the Standard Model is the proper starting point for the search beyond it. You cannot recognize something new unless you understand what the known theory predicts. A new particle is not discovered simply because a detector sees a strange flash. Detectors see many strange flashes. Nature is noisy. Machines are complicated. Background processes can imitate signals. To find new physics, scientists must first calculate, with great care, what the standard model says should happen. Only then can they notice when reality gives a slightly different answer. The standard model is both the foundation and the measuring stick. It is the thing we may need to go beyond, and the thing that tells us where beyond might begin. So before we wander into dark matter candidates, sterile neutrinos, supersymmetric partners, axions, and other possible hidden residents of the universe, it is worth resting here for a moment with the known particles. They are strange enough already. Quarks that never appear alone, neutrinos that pass through worlds, photons that carry light, gluons that bind the heart of matter. A Higgs field spread through space, giving mass to particles as naturally as air gives resistance to a moving hand. This is not a dull rule book. It is a compact description of a universe far more delicate and intricate than everyday experience suggests. And yet, the very success of this tiny rulebook has led us to the next question. If the standard model explains so much, why does the universe still seem to be whispering that something is missing? The answer begins with the gaps it leaves behind, not empty gaps of ignorance, but precise, well-shaped gaps that point toward deeper possibilities. The particles we know form the visible grammar of matter, but the sentences written across the cosmos may require words we have not learned yet, and that is where the story begins to move from the known list of particles toward the hidden spaces around it. Now that we have met the standard model as the universe's tiny rulebook, we can begin looking more closely at the particles inside it, not as names on a chart, but as the working ingredients of reality. This is where the story becomes both wonderfully clear and quietly puzzling, because the particles we know are not random little specks scattered through theory. They form a pattern, a very successful pattern. A pattern so reliable that it has helped physicists predict what should happen in experiments with astonishing precision. And yet, as soon as we begin to understand the pattern, we also begin to notice the empty spaces around it. The known particles fall into a few main groups. There are the matter particles, the particles that make up the stuff of the world, and there are the particles that carry forces, allowing matter to interact. At the centre of ordinary matter are quarks and leptons. Quarks combine to form protons and neutrons. Protons and neutrons gather into atomic nuclei. Electrons, which are leptons, surround those nuclei and help form atoms. Atoms join into molecules. Molecules build dust, water, air, skin, wood, glass, tea, toast, and the slightly mysterious crumbs that appear on a desk, even when nobody remembers eating there. From a small collection of particles, the enormous variety of the everyday world emerges. That alone is remarkable. Think about how many different things exist in the visible world. A snowflake, a pine tree, a whale, a cathedral window, a sleeping cat, a thundercloud, a spoon left in a sink. They feel completely different. They behave differently. They smell different, sound different, and have very different opinions about being pushed off a table. But underneath all that variety, the same small set of particles keeps appearing. Electrons, up quarks, down quarks, photons, gluons. The ordinary world is not made from millions of separate basic ingredients. It is made from a few, arranged in an almost impossible number of ways. Nature is very good at getting variety from simplicity. Humans do something similar with alphabets, music notes, or recipes, though nature manages it without losing the measuring spoon. The electron is perhaps the easiest fundamental particle to appreciate, because it plays such a direct role in the world we touch. Electrons help determine how atoms bond with one another. They are responsible for much of chemistry. They carry electric current through wires. They absorb and emit light. Their arrangement around atoms helps explain why some materials conduct electricity, why others insulate, why metals shine, why salt dissolves in water, and why your phone charger becomes a small object of panic when it goes missing. The electron is not large, not visible, not something you can point to under an ordinary microscope, but it is everywhere in the story of ordinary life. Then there are the quarks. Inside every proton and neutron are quarks held together by the strong force. The two quarks most important for ordinary matter are called up quarks and down quarks. They combine in different arrangements to make protons and neutrons. These names, up and down, are not descriptions in the everyday sense. An up quark is not physically sitting above a down quark like two people on a bunk bed. Particle names often sound as if someone was choosing labels late at night and perhaps getting a little tired. But the label stuck, and now we have a universe built partly from things called up and down quarks, which is at least easier to say than some alternatives. Quarks are unusual because they are confined. You do not find a single quark drifting around alone in ordinary conditions. Try to pull quarks apart, and the energy involved does not simply free one like pulling a bead from a necklace. Instead, the strong force behaves in a way that tends to create new particles, rather than allowing an isolated quark to escape. This is very different from the way electrons can move through a material, or photons can travel across space. Quarks are fundamental, but they are also hidden inside larger particles. They are like the beams inside a wall. You do not usually see them, but the whole structure depends on them. The standard model also includes heavier relatives of these everyday particles. The electron has heavier cousins called the muon and the tau. The up and down quarks have heavier relatives as well. These particles do not make up stable ordinary matter because they decay quickly into lighter particles. They appear in high energy conditions such as cosmic ray collisions in the atmosphere or particle accelerator experiments. It is tempting to ask why they exist at all. If the first generation of particles is enough to make atoms, stars, planets, and people, why did nature include 2 more generations? Was it necessary? Was it a leftover from some deeper structure? Is there a hidden reason? Or did the universe simply decide that one family was too tidy and added a couple of heavier copies for flavour? The standard model does not give a deep answer to that question. It includes the generations and describes how they behave, but the reason for the pattern remains unclear. This is one of those places where the theory works beautifully and still leaves you staring at it with narrowed eyes. It is a bit like finding 3 sets of keys on a table. One opens every door you normally use, the other 2 are heavier, stranger, and mostly kept in a drawer. But they are clearly part of the same collection. You can label them, you can weigh them, you can test them, but you still wonder who made the extra sets and why. Neutrinos add another layer of strangeness. They're also matter particles, but they barely interact with the world. They are produced in enormous numbers by the sun, by nuclear reactions, by exploding stars, and by processes that occurred in the early universe. They pass through matter with astonishing ease. Every second, countless neutrinos pass through your body, through your room, through the planet, and onward, usually without leaving any trace at all. If most particles are guests at the party of matter, neutrinos are the ones slipping through the back wall without touching the furniture. For a long time, neutrinos seem to fit into the standard model as massless particles. Then, experiments showed that neutrinos can change from one type to another as they travel. This behaviour, called neutrino oscillation, means they must have mass. Tiny mass, yes, but mass all the same. That discovery was not just a small correction. It was a sign that the original standard model was incomplete. It could be extended to include neutrino masses, but the deeper explanation is still open. Why are neutrino masses so small compared with the masses of other particles? Do they get their mass in the same way as other particles, or through some different mechanism? Are there hidden neutrino-like particles that do not interact through the known forces at all? These questions are not decorative. They may point toward an entire doorway beyond the known particle list. Alongside the matter particles, we have the force carriers. The photon carries the electromagnetic force. Gluons carry the strong force. Other heavy force-carrying particles are involved in the weak interaction. These particles help explain how matter interacts. When an electron responds to an electromagnetic field, when quarks are bound inside protons, When certain particles decay into lighter ones, the force carriers are part of the description. Again, these are not little messengers flying around like tiny postal workers with satchels, though that picture can be charming for about 3 seconds. In the deeper theory, they are excitations of fields, and interactions arise from the way those fields relate to one another. Then there is the Higgs boson, the particle connected with the Higgs field. The Higgs field is present throughout space, and is deeply tied to why many fundamental particles have mass. The discovery of the Higgs boson confirmed a major part of the Standard Model, but it also made some questions sharper. The Higgs is not just a final piece that completed the puzzle and allowed everyone to go home for a quiet cup of tea, it is also a clue. Its measured properties fit the Standard Model very well, but physicists still wonder why the Higgs field has the values it has, why the Higgs boson is as light as it is compared with certain theoretical expectations, and whether the Higgs might connect to particles we have not yet discovered. In other words, finding the Higgs did not end the story. It made the next page harder to ignore. One gap left by the known particles is dark matter. This is perhaps the most famous missing piece. The particles in the Standard Model can account for the matter we see directly, the matter made from atoms, stars, gas, dust, and living things. But astronomical evidence strongly suggests that there is much more matter than this. Galaxies rotate as if they are embedded in invisible halos of mass. Galaxy clusters behave as if unseen matter is holding them together. Light from distant objects bends as if it is passing through gravitational fields created by material we cannot see. The early universe also carries patterns that point towards dark matter. Whatever it is, it appears to be a major part of the cosmic structure. The Standard Model does not contain a good dark matter particle. Neutrinos are real and hard to see, but the known neutrinos are not enough to explain the dark matter that shapes galaxies. They are too light and too fast-moving to build the kind of cosmic structure we observe. So, if dark matter is made of particles, those particles are not part of the usual Standard Model family. They would be new, beyond the known list. Perhaps they interact through gravity and only very weakly, if at all, through the other forces. Perhaps they belong to a hidden sector, a whole set of fields and particles that mostly ignore ordinary matter. That idea sounds dramatic, but in a way it is modest. We already know of particles like neutrinos that barely interact with us. Dark matter may simply be even better at keeping to itself. Another gap is gravity. Gravity is the force we experience most obviously in daily life. It keeps our feet on the ground, guides planets around stars, pulls stars into galaxies, and shapes the large-scale structure of the universe. Yet gravity is not part of the Standard Model. The Standard Model describes the other fundamental interactions in the language of quantum fields, but gravity is described by general relativity, where mass and energy curve space and time. Both descriptions work extremely well in their own domains, but they do not yet fit together into one complete quantum theory of gravity. Many physicists suspect that a full quantum theory of gravity might involve a particle called the graviton, a hypothetical carrier of the gravitational interaction. But no graviton has been detected, and the problem is far deeper than simply adding one more name to the particle list. Gravity may require a new framework altogether. The absence of gravity from the Standard Model is not usually a problem when calculating particle interactions in accelerators, because gravity is extremely weak at the scale of known particles. You can safely ignore it in many laboratory settings, the way you might ignore the gravitational pull of a biscuit while deciding whether to eat it. Technically it is there. Practically other forces matter far more. But in the earliest universe, where energies were enormous and densities were extreme, quantum effects and gravity may have been tangled together. Near black holes, the same issue appears. To understand those extreme settings fully, the Standard Model is not enough. The matter and antimatter imbalance is another puzzle. The Standard Model includes antimatter. Antimatter particles have the same mass as their matter partners, but opposite electric charge and related properties. When matter and antimatter meet, they can annihilate into energy. In the early universe, matter and antimatter should have been produced together. So why is the universe today filled mostly with matter? Why did matter survive? Why was there not complete cancellation, leaving behind a universe with light but almost no atoms? The Standard Model contains some ways in which matter and antimatter behave differently, but these do not appear strong enough to explain the enormous matter dominance we observe. Something more may have happened, perhaps involving particles or interactions beyond the Standard Model. This is a quiet but profound point. Our existence depends on a small excess of matter over antimatter in the early universe. If the balance had been exact, the story would have gone very differently. There would be no carbon, no oxygen, no planets, no seas, no warm rooms at night, no one wondering about particle physics while trying to drift off. A tiny cosmic imbalance became everything. The Standard Model acknowledges parts of the mechanism, but not enough of it. Somewhere in the deeper story of particles there may be an explanation for why anything remained at all. There is also the puzzle of masses. The particles we know have very different masses. The electron is light compared with the muon and tau. Neutrinos are far lighter still. Quarks span a wide range, with the top quark being especially heavy. The Standard Model can use these masses once they are measured, but it does not fully explain why they take the values they do. The numbers are not predicted from first principles within the model. They are inserted into it. This does not make the theory wrong. Many useful theories contain measured values, but it leaves the impression that the Standard Model may be describing the surface of a deeper structure, one in which these values might one day make more sense. A similar feeling comes from the way the forces differ. The electromagnetic force, weak force, and strong force have different strengths and behaviours at ordinary energies. But in the early universe, at much higher energies, some of these forces may have been more closely connected. The electromagnetic and weak forces are already understood as different low-energy expressions of a more unified electro-weak interaction. That success makes physicists wonder whether the strong force might also join the pattern at still higher energies, and whether a deeper unification may exist. If so, new particles might be part of the story. They could have been important in the early universe, even if they are too massive or too weakly interacting to appear in ordinary conditions now. Then there is the question of why the Higgs field is stable in the way it appears to be. Without going into mathematical details, the Higgs seems delicately placed. Some theoretical arguments suggest that the Higgs mass should be strongly affected by high-energy physics, yet it remains at the value we observe. This has led physicists to propose ideas such as supersymmetry, in which every known particle has a partner particle with different properties. Supersymmetry could help stabilize the Higgs and might even provide a dark matter candidate. But so far, experiments have not found the expected partner particles. This does not completely rule out the idea, but it makes the simplest versions harder to maintain. The universe, as usual, is not obligated to choose the option physicists find most convenient. It is worth noticing how careful scientists have to be here. A gap in a theory is not the same as evidence for one particular new particle. Dark matter does not automatically mean a certain candidate is real. Neutrino mass does not automatically prove sterile neutrinos exist. The Higgs puzzle does not automatically mean supersymmetry is correct. The matter-antimatter imbalance does not tell us exactly which new interaction caused it. The gaps are invitations, not confirmations. They tell us where to look, but not what we will find. Physics is full of possible answers standing politely in line, waiting for experiments to decide who actually gets through the door. Still, the known particles leave these gaps in a way that is too important to ignore. The Standard Model is not an old theory failing loudly. It is a successful theory ending quietly before the whole story is told. That is a very different situation. If a theory fails everywhere, you throw it away. Throw it. If it succeeds almost everywhere but cannot explain a few crucial facts, you study the edges. You look at the places where the success stops. You ask whether the edge is a wall, a window, or the beginning of another room. The particles we know are already strange enough to stretch the imagination. Electrons do not orbit nuclei like tiny planets in a simple solar system. Quarks are confined inside protons and neutrons. Neutrinos pass through almost everything. Force carriers arise from fields. The Higgs field fills space. Antimatter exists. Particles can appear and disappear in interactions as long as the proper conservation rules are obeyed. Even the familiar world rests on foundations that do not behave like ordinary objects. So when physicists suggest that there may be more particles beyond the standard model, they are not making the universe stranger than it already is. They are admitting that the known strangeness may not be complete. A useful way to think about it is to imagine standing in a room at night with a lamp on. The objects in the circle of light are clear. You can see the table, the chair, the book, the cup. You can describe them carefully. You can measure their positions. You can learn a great deal about the room. But the edges of the light are not the edges of the room. The darkness beyond them may be empty, or it may contain more furniture, a doorway, a sleeping dog, or a pile of laundry that has been waiting with great patience. The standard model is the circle of light. It shows us what we can currently describe with great precision. The gaps are the shadows that suggest the room may continue, and those shadows are not vague feelings. They come from measurements. Galaxy rotation curves, gravitational lensing, cosmic background patterns, neutrino oscillations, particle masses, precision tests, matter-antimatter imbalance, the absence of a quantum theory of gravity. Each one is a different kind of clue. Some are cosmic, written across galaxies. Some are microscopic, hidden in particle behavior. Some are theoretical, arising from the structure of the model itself. Together, they make the search beyond the standard model one of the central efforts in modern physics. Yet there is a gentle humility in all of this. We may discover one new particle and find that it solves a major problem, or we may discover an entire hidden sector, or we may discover that some of our assumptions were wrong and that the answer is not a particle in the usual sense. The history of physics is full of surprises that seemed obvious only afterward. Before the electron was discovered, atoms looked indivisible to many. Before the neutrino was detected, it seemed almost like a desperate accounting trick. Before the Higgs boson was found, it lived for decades as a prediction. The unknown does not stay unknown because it is unimportant. Sometimes it stays unknown because it is quiet. For now, the known particles give us both confidence and restlessness. Confidence, because the standard model works with astonishing power. Restlessness, because it leaves behind questions too large to ignore. The ordinary world is built from particles we know, but the universe as a whole seems to require more than ordinary matter. The laws we have are reliable, but their pattern looks unfinished. The list is accurate, but perhaps not complete, and if there are missing particles, they may not be rare decorations added to the edge of physics. They may be central to why galaxies exist, why matter survived, why neutrinos have mass, and why the forces of nature take the forms we observe. So we carry the known particles with us as the foundation, but we do not stop with them. We let the gaps guide us. And the largest, most persistent gap of all is the invisible mass that shapes the cosmos, the dark matter that holds galaxies in its quiet grip while refusing to shine, reflect, or introduce itself properly. If any mystery has made physicists suspect a hidden particle world, it is this one, the unseen guest at the cosmic table, present in the gravity of the universe but absent from the standard model's neat little list. There is a particular kind of mystery that does not announce itself by glowing, exploding, ringing a bell, or politely stepping into view. It is the kind of mystery that reveals itself only by what it does to everything around it. Dark matter is like that. It does not shine. It does not seem to reflect light. It does not gather into stars or lamps or warm little planets with weather and kitchens. It does not introduce itself through ordinary chemistry, and it has never been caught sitting neatly inside a detector with a name tag saying, "Hello, I am the missing mass of the universe." That would be helpful, of course, but the universe is rarely that considerate. Instead, dark matter is known by its gravity. It pulls, it shapes, it gathers. It leaves fingerprints not in light, but in motion. Stars move as if something unseen is holding them. Galaxies rotate as if they are wrapped in invisible weight. Clusters of galaxies bend the path of light from objects far behind them, like a glass lens made not of glass but of gravity. The largest structures in the universe seem to have formed with the help of a hidden scaffolding, something that did not shine itself but helped ordinary matter collect, cool, and eventually make the bright things we can see. Dark matter is invisible in the usual sense, but it is not absent. It is the quiet guest at the cosmic table, eating nothing, saying nothing, but somehow affecting where all the chairs are placed. To feel why dark matter became such a serious idea, imagine watching a merry-go-round in a park at night. You can see a few lights attached to its edge, moving around in circles. From the speed of those lights, you can estimate how much mass must be inside the structure to hold everything together. If the lights are moving very fast, you expect there to be a strong central support, a heavy frame, something solid keeping the whole thing from flying apart. Now imagine that you look carefully and find that the visible frame is far too light. The lights are moving too quickly for the amount of structure you can see. Something is missing. Either your understanding of motion is wrong, or there is hidden mass keeping the system together. This is roughly the situation astronomers found with galaxies. In a simple expectation, stars farther from the centre of a galaxy might be expected to move more slowly, because most of the visible mass is concentrated nearer the middle. In our solar system, for example, planets farther from the Sun move more slowly than planets close in. But galaxies did not behave quite so neatly. Stars far from galactic centres were often moving faster than visible matter alone seemed able to explain. The outer stars were not drifting away into space. They remained bound, moving as if the galaxy contained much more mass than telescopes could see. Something was holding the system together. This was not a small mismatch, like realizing you forgot to carry the 1 in a bit of cosmic arithmetic. It was a large and repeated clue. Galaxy after galaxy seemed to suggest the same thing. There was more gravitational influence than visible matter could account for. One possibility was that galaxies were surrounded by vast halos of unseen matter. Not a thin ring, not a small hidden clump, but a broad, extended presence reaching far beyond the bright disk of stars. The visible galaxy, the glowing spiral or soft elliptical shape we admire in images, might be only the shining centre of a much larger dark structure. That idea changes the way we picture galaxies. A galaxy is not merely a pinwheel of stars floating in emptiness. It may be more like a lantern glowing inside a large invisible cloud. The lantern is what we see. The cloud is what gravity feels. The stars trace only the luminous part of the system, while dark matter forms a wider halo around it. The bright galaxy is beautiful, but it may be only a small portion of the full gravitational object. It is a little like seeing a person walk through fog carrying a candle. You see the candlelight and maybe a hint of a hand, but not the full person moving through the mist. Dark matter also appears in the way galaxy clusters behave. Galaxy clusters are enormous collections of galaxies bound together by gravity. They contain galaxies, hot gas, and apparently a great deal of unseen mass. Long before modern dark matter maps, astronomers noticed that galaxies inside some clusters moved too quickly to be held together by the visible matter alone. Later observations of hot gas and gravitational lensing strengthened the case. Gravitational lensing is one of the most elegant clues in this story. According to general relativity, mass bends space and time, and light follows those curves. So when light from a distant galaxy passes near a massive cluster on its way to us, its path can bend. The cluster acts like a natural cosmic lens. By studying how background galaxies are distorted, stretched, or multiplied, astronomers can map where the gravitational mass lies. This is wonderfully strange. We cannot see dark matter directly, but we can see how it bends the light of things behind it. It is like noticing a clear glass bowl on a table because the wallpaper behind it looks warped. The bowl itself may be transparent, but the distortion gives it away. In the case of dark matter, the bowl is not made of glass, and the table is the universe, which does make the kitchen metaphor work rather hard. But the basic idea remains gentle enough. Invisible mass can be mapped through the visible bending of light. One famous kind of evidence comes from collisions between galaxy clusters. When clusters pass through each other, the hot ordinary gas can slow down, collide, and separate from the galaxies. Dark matter, if it interacts very weakly except through gravity, should pass through more easily. In some observed systems, the gravitational mass appears offset from the hot gas, as if most of the mass moved with the collisionless component rather than with the ordinary matter. This is often treated as strong evidence that dark matter is not just a bookkeeping mistake, but a real form of matter behaving differently from atoms. It is not a perfect cartoon, and the details are complex, but the basic lesson is clear. The gravity seems to be where the visible ordinary matter is not. Dark matter also matters for the early universe. After the Big Bang, the universe was hot, dense, and expanding. Ordinary matter interacted with radiation, which made it difficult for it to clump too quickly. Dark matter, if it did not interact strongly with light, could begin forming gravitational wells earlier. These wells would help draw ordinary matter inward later, guiding the growth of galaxies and clusters. In this picture, dark matter is not just an extra ingredient sprinkled onto finished galaxies. It is part of the architecture that allowed cosmic structure to form. It helped create the invisible framework into which ordinary matter eventually fell. That is a remarkable thought. The stars we see may have formed partly because something unseen prepared the stage. The galaxies that decorate telescope images may owe their shapes, histories, and locations to a substance that has never touched light in the ordinary way. The universe might be luminous only because darkness gave it a place to gather. That sounds almost poetic, but it is also a serious scientific possibility. The bright universe and the dark universe are not separate stories. They are woven together by gravity. So what could dark matter be? This is where the question of particles beyond the standard model becomes very direct. If dark matter is made of particles, those particles do not fit the known list. They cannot simply be electrons, protons, neutrons, or ordinary atoms that are too dim to see. Astronomers have considered many ordinary possibilities over time. Could dark matter be faint stars, cold gas, black holes, or other compact objects? Some of these may contribute a little in certain places, but they do not seem able to explain the full amount and behaviour of dark matter across the universe. The evidence points towards something more unfamiliar, something not made of ordinary atomic matter. The known neutrinos are also not enough. Neutrinos are real, abundant, and difficult to see, which makes them tempting suspects at first. They are like particles that already have the right mood for a mystery. But ordinary neutrinos are too light and too fast-moving to form the kind of dark matter structure needed to explain galaxies and cosmic growth. They would smooth things out too much. The universe we observe appears to require dark matter that was relatively slow-moving in the early stages of structure formation, often called cold dark matter in the language of cosmology. The word cold here does not mean chilly like a forgotten cup of tea. It means moving slowly compared with the speed of light in the early universe. A very specific kind of cold, and not one solved by a blanket. For many years, one of the most popular ideas was that dark matter might be made of particles that interact through gravity, and perhaps through the weak nuclear force, but not through electromagnetism. Such particles would not shine or absorb light, but they might occasionally bump into ordinary matter in ways detectors could catch. These hypothetical particles are often called weakly interacting massive particles. They became attractive because they could naturally appear in certain theories beyond the standard model, and could have been produced in the early universe in roughly the right abundance. It was a neat idea, perhaps too neat for nature's taste, but still powerful enough to inspire decades of experiments. To search for such particles, scientists have built detectors deep underground. The underground setting matters because the surface of Earth is constantly showered by cosmic rays and other background particles. A dark matter signal, if it exists, would be rare and subtle, so experiments need quiet, really quiet. Mines, tunnels, and deep laboratories become places where physicists wait for a tiny interaction between a dark matter particle and an ordinary atom. The detector may contain liquid xenon or other carefully chosen materials. The hope is that, once in a great while, a dark matter particle passing through Earth will collide with a nucleus and leave a tiny flash or vibration. It is a little like sitting in a dark room for years, waiting for one almost silent knock from a visitor who may not use doors. So far, these direct searches have not produced a confirmed dark matter particle. That absence is important. It does not mean dark matter is not real. It means certain possible particles and certain interaction strengths are becoming less likely. Each experiment narrows the territory. It says, if dark matter is this kind of particle, it does not interact this strongly in this mass range. The map of possible answers becomes more constrained. This can feel frustrating, but it is progress. Science often advances by learning where the answer is not. The universe may be hiding, but the hiding places become fewer. Another strategy is to look for dark matter annihilation or decay. If dark matter particles can collide with each other and produce ordinary particles, or if they can decay into detectable signals, then telescopes might see unusual radiation from places where dark matter is dense, such as the centers of galaxies or dwarf galaxies. Scientists search for excess gamma rays, cosmic ray particles, or other signatures that might point to dark matter. The difficulty is that the universe has many ways to produce energetic signals. Pulsars, black holes, supernova remnants, and ordinary astrophysical processes can imitate or obscure the possible signs. It is not enough to see something unusual. One must show that it cannot be explained by known sources. The universe is very good at making background noise. If it had a hobby, it might be confusing detectors. Particle colliders offer another path. If dark matter particles can be produced in high-energy collisions, they might escape the detector unseen, carrying away energy and momentum. Physicists would then infer their presence from an imbalance in the visible collision debris. This is another version of seeing the invisible through what is missing. You smash known particles together, watch what comes out, and notice whether something seems to have slipped away. Again, no confirmed dark matter particle has appeared yet. But collider searches help test theories and narrow possibilities. The fact that dark matter is invisible does not make it unreachable. It only makes the search more indirect, more patient, and perhaps a little more like detective work in a room where the suspect has excellent manners and leaves very few footprints. There are also lighter candidates such as axions. Axions were originally proposed for a different problem in particle physics, but they turned out to be possible dark matter candidates as well. If they exist, they would be extremely light and very weakly interacting. Instead of behaving like heavy particles occasionally bumping into atoms, axions might behave more like a faint field spread through space, with subtle effects that special experiments could detect. Some searches use powerful magnetic fields, hoping to convert axions into photons under the right conditions. Others use resonators or precision measurement techniques. Axion experiments feel almost musical in spirit, tuning instruments to hear a hidden note in the dark. There may also be dark photons, sterile particles, hidden sector particles, or other candidates that interact with ordinary matter through tiny portals. The phrase hidden sector sounds dramatic, like a secret department in a cosmic government building, but it simply means a set of particles and forces that do not interact strongly with the standard model particles. They might have their own interactions, their own structure, perhaps even a kind of dark complexity. This does not mean dark matter forms shadow planets or dark people, or anything so imaginative. Most models are far more restrained. But the possibility reminds us that the standard model may describe our visible sector, while another sector remains mostly unseen. It is also possible that dark matter is not a new particle at all. Some scientists explore modifications of gravity, asking whether our understanding of gravitational behaviour changes on galactic or cosmic scales. These ideas try to explain galaxy rotation and other observations without adding large amounts of unseen matter. They face serious challenges, especially in explaining the full range of evidence from lensing, galaxy clusters, and the early universe, but they remain part of the broader scientific conversation. This is healthy. A mystery this large should be examined from more than one angle. Still, the particle dark matter idea remains compelling because it can connect many different observations in a relatively unified way. The most widely used cosmic picture today includes dark matter as a major component of the universe. In that picture, dark matter forms halos around galaxies, helps seed structure, and shapes the cosmic web. Ordinary matter falls into the gravitational wells created by dark matter, forming stars and galaxies inside a larger dark framework. The cosmic web itself, with galaxies arranged along filaments and clusters like knots, may trace the invisible skeleton of dark matter beneath the luminous surface. If you have ever seen an image of city lights at night from above, with bright clusters connected by roads, you can imagine something similar on a cosmic scale, except the roads are gravitational structures and the lights are galaxies. The dark framework is not visible, but the bright matter reveals its outline. There is a deep irony here. The standard model describes the particles that make up everything we directly touch, see, and use. It explains the matter of our bodies and our planet, and yet that matter may be only a smaller part of the total matter in the cosmos. The familiar particles, the ones that build atoms and chemistry, may not be the dominant material in the universe. We live in the visible minority. That is humbling, but also rather lovely in its own way. It means the everyday world is not the whole story. The table, the stars, the moon, the bones in your hand, the oxygen in the room, all of it may be made from a special kind of matter that happens to interact with light, while most matter remains silent. This does not make ordinary matter unimportant, quite the opposite. Ordinary matter is the matter that cools, collapses, forms stars, builds planets, and eventually asks questions about dark matter. It may be less abundant than dark matter, but it is chemically rich, it is bright, it is talkative, it forms oceans and nervous systems and telescopes. Dark matter, for all its gravitational power, seems unable to do many of those things, at least in the simple models. It does not easily shed energy by emitting light, so it does not collapse into dense disks and stars the way ordinary matter can. It stays diffuse, forming halos rather than glowing objects. It is the quiet framework, not the candle flame. And yet, without that framework, the bright world may have formed very differently. Galaxies might not have grown as they did. The cosmic web might not have developed the same way. The universe may have lacked the gravitational scaffolding needed to build structure on time. Dark matter, if it is truly there as a particle substance, has been shaping the story from the beginning while remaining almost completely hidden from our senses. It is hard not to admire that level of subtle influence. Most things that shape history want a statue. Dark matter shaped galaxies and did not even ask for a plaque. The search for dark matter is therefore not just about filling in a missing number. It is about discovering what most of the matter in the universe may actually be. It is about learning whether the standard model is only one visible island in a larger particle ocean. It is about asking whether the universe has hidden fields, hidden forces, hidden families, or a single elusive particle that has quietly guided cosmic structure for billions of years. Each experiment that listens for dark matter is part of this larger question. Each telescope map, each underground detector, each collider search, each careful calculation is another way of asking, what are you? For now, dark matter remains unnamed in the deepest sense. We have a role, but not an actor. We have gravitational effects, but not a confirmed particle. We have a place at the table, but not a face across from us. That is why it sits so powerfully in the story of physics beyond the standard model. The known particles cannot do the job. Something else seems necessary. And whether that something is a heavy particle, a light axion, a sterile hidden state, a whole dark sector, or a clue that gravity itself needs a revision, the mystery pulls us beyond the boundaries of the tiny rulebook we already have. There is a calmness in that uncertainty if we let it be calm. The universe is not empty where it looks dark. The silence between galaxies may be structured. The invisible may be active. The darkness may not be a blank, but a presence that gravity can read even when light cannot. And once we become comfortable with that idea, it becomes easier to meet another kind of nearly invisible particle, one that we already know exists, one that streams through us constantly, one that forced physicists to revise their expectations, and one that may have even stranger hidden relatives waiting somewhere beyond the known list. Neutrinos are among the strangest particles we know, which is saying something in a universe that already contains quarks, gluons, antimatter, black holes, and people who enjoy setting alarms for 5 more minutes. They are real particles, firmly part of modern physics, and yet they behave almost like rumours. They pass through matter with such ease that the word particle begins to feel too solid for them. Every second, vast numbers of neutrinos move through your body, through the walls around you, through the ground beneath you, and through the entire Earth as if the planet were hardly there. They do not ask permission, they do not knock, they do not warm the room, shake the floor, or leave little footprints on the carpet. They simply pass through, silent and nearly untouchable. That is why neutrinos are such a good place to continue the search beyond the standard model. They sit in a strange position. On one hand, they are known particles. We have detected them. We have measured their behaviour. We know they are produced by the sun, by nuclear reactions, by radioactive decays, by exploding stars, and by violent cosmic processes. On the other hand, neutrinos have already shown us that the original standard model was not complete. They were expected, in the simplest version of the theory, to have no mass. Then, nature quietly disagreed. Not loudly, not rudely, just with enough evidence to make physicists rewrite part of the story. Neutrinos can change from one type into another as they travel, and that changing means they must have mass, however tiny. So these ghostly little particles are not just odd members of the known family. They are messengers from the edge of what the known family can explain. The word neutrino means little neutral one, which is a charming name for something so difficult to catch. It is neutral because it has no electric charge. That already makes it harder to detect than a charged particle like the electron. Charged particles interact strongly with electromagnetic fields. They leave tracks more easily. They respond to magnets. They make their presence known. Neutrinos do not. They interact through the weak nuclear force and through gravity, and gravity is far too weak at particle scales to help us much in the laboratory. The weak force, true to its name, gives neutrinos only a very small chance of interacting with ordinary matter. This is why they can cross enormous distances of solid material without noticing. A neutrino could pass through a wall, a mountain, or a planet, and most of the time nothing would happen. It would not collide with an atom in the familiar sense. It would not scatter like a tennis ball bouncing from a racket. It would simply continue. If ordinary matter were a crowded city, neutrinos would be so small and so unsociable that they could walk from one side to the other without bumping into anyone, even at rush hour. This makes them frustrating to study, but it also makes them precious, because neutrinos can escape from places that light cannot easily leave. They can carry information from the heart of the sun, from the collapse of a star, from nuclear reactions deep inside matter, and perhaps from the early universe itself. The story of neutrinos began with a problem. In certain radioactive decays, energy seemed to be missing. Physicists are not fond of missing energy. It is the sort of thing that makes them put down their tea and look serious. The rules of physics suggested that energy should be conserved, but the measurements did not seem to add up if only the visible particles were included. One possible solution was that an unseen particle was carrying away the missing energy. This was a bold idea, because the particle would have to be neutral, very light, and extremely difficult to detect. It was proposed almost as a desperate rescue of conservation, a tiny invisible accountant leaving the room with the missing balance. For years, the neutrino remained more prediction than direct observation. It was as if physics had written a character into the script and then waited decades for the actor to appear on stage. Eventually, neutrinos were detected from nuclear reactors, confirming that the missing particle was not just a useful invention. It was real. Later, neutrinos from the Sun were observed, and this opened one of the most important puzzles in particle physics. Scientists had models of how the Sun produces energy through nuclear fusion. Those models predicted how many solar neutrinos should reach Earth. But early experiments detected fewer than expected. Quite a few fewer. Either the Sun was not working the way physicists thought, which would have been awkward for many reasons, or something was happening to the neutrinos on their journey. This became known as the solar neutrino problem. It lasted for decades. The Sun appeared to be sending fewer electron neutrinos than expected. The answer turned out to be wonderfully strange. The missing neutrinos were not really missing. They had changed identity. Neutrinos come in different types, often called flavors. There are electron neutrinos, muon neutrinos, and tau neutrinos. A neutrino created as one type can later be detected as another type. It can oscillate, shifting its identity as it travels through space. This is not like changing a coat or deciding to use a different name at a hotel. It is a quantum process, tied to the fact that the states connected with neutrino flavor are not the same as the states connected with neutrino mass. We do not need the technical details here. The important point is that neutrinos are not fixed in the simple way we might expect. They change as they move, and that change carries a profound implication. For neutrinos to oscillate, they must have mass. Very tiny masses, but not zero. This was one of the clearest signs that the original standard model needed revision. The model could include neutrinos, but it had treated them as massless in its simplest form. Nature, with its usual quiet sense of drama, said otherwise. The neutrino had once been invented to solve a problem of missing energy. Then it created a new problem of its own. It is rather like inviting someone to a dinner party because they can explain why the soup vanished, only to discover they have also rearranged the furniture while nobody was looking. The smallness of neutrino mass is itself a mystery. Compared with charged leptons and quarks, neutrinos are incredibly light. Why? Are they light because they receive mass through a different mechanism? Are they connected to heavy unseen particles that existed in the early universe? Are they their own antiparticles, in a deep and unusual sense? These are not small questions. They may connect neutrinos to some of the largest mysteries in cosmology, including the matter-antimatter imbalance and the possible existence of particles beyond the standard model. One idea that appears in this landscape is the sterile neutrino. The name sounds as if it belongs in a very clean hospital corridor, but in particle physics it means something specific. A sterile neutrino would be a neutrino-like particle that does not interact through the weak nuclear force in the usual way. It would not feel the electromagnetic force because neutrinos are neutral. It would not feel the strong force, and if it also did not feel the weak force, then it would be even harder to detect than the neutrinos we already know. It would interact mainly through gravity, and perhaps through subtle mixing with ordinary neutrinos. In other words, if normal neutrinos are ghosts, sterile neutrinos are ghosts standing behind other ghosts and refusing to wave. Why would anyone propose such a thing? One reason is that neutrino mass may be easier to understand if there are additional neutrino states beyond the 3 known active types. These hidden states could help explain why ordinary neutrinos are so light. In some theoretical pictures, very heavy sterile neutrinos from the early universe could play a role in generating the tiny masses we observe today. In other versions, lighter sterile neutrinos might show up through anomalies in experiments, small mismatches in how neutrinos appear and disappear, There have been hints over the years from certain short-distance experiments that seem to suggest something more complicated than the three-neutrino picture. But hints are not discoveries. Some results have supported the possibility. Others have placed strong limits on it. The field remains careful, unsettled, and very much alive. Sterile neutrinos are also interesting because they could, in some mass ranges, be connected to dark matter. A sterile neutrino dark matter particle would be far less interactive than ordinary matter and could help account for unseen mass in the universe, depending on its properties. It would not be the same as the heavier weakly interacting candidates often discussed in dark matter searches. It would belong to a different kind of possibility, one tied to the neutrino sector. If such particles exist, they might have influenced the formation of cosmic structure, or left faint signals in astrophysical observations, but again, the evidence is not settled. The universe has not yet handed us a clear answer, only a collection of clues that may or may not belong to the same hidden object. This is what makes neutrino physics so important. It is not merely a side street off the main road of particle physics. It may be one of the roads that leads out of the known city entirely. Neutrinos already force us to add something beyond the simplest standard model. Their masses are real. Their oscillations are real. The question is what those facts are trying to tell us. Are they small adjustments, easily added without changing the larger structure? Or are they the visible tips of a deeper system, involving heavy particles, hidden states, and early universe processes that shape the matter around us? To study neutrinos, physicists have built some of the most remarkable detectors on Earth. Many are placed deep underground or under mountains to reduce background noise from cosmic rays. Some use enormous tanks of water, watched by sensitive light detectors. When a neutrino very rarely interacts with matter inside the tank, it can produce a charged particle moving through the water. That charged particle may create a faint cone of light, which detectors can record. From that light, physicists infer the neutrino's properties. This is an extraordinary act of patience. Imagine trying to learn about invisible birds by filling a dark cavern with water and waiting for one of them to brush the surface once every so often. It sounds unreasonable until it works. Other detectors use ice, liquid argon, scintillator materials, or giant volumes of carefully monitored substance. Some experiments study neutrinos from reactors. Others use beams of neutrinos produced by accelerators and send them across long distances through Earth to detectors far away. The neutrinos do not need a tunnel. They pass through the ground directly, which is convenient, though still slightly rude if you think about it. By comparing the neutrinos produced at the source with the neutrinos detected after travelling, scientists can study how they change flavour. These long baseline experiments are designed to measure the details of neutrino oscillation, the ordering of neutrino masses, and possible differences between neutrinos and antineutrinos. That last point matters deeply. If neutrinos and antineutrinos behave differently in certain ways, it might help explain why the universe contains more matter than antimatter. The known differences in the standard model do not seem sufficient to account for the cosmic imbalance. Neutrinos may offer another route. Perhaps in the early universe, heavy neutrino-like particles decayed in ways that favoured matter over antimatter, leaving behind the slight excess from which everything later formed. This idea has different versions and none is confirmed, but it shows how these tiny particles could be connected to one of the biggest facts of existence. The matter in your body, the atoms in Earth, the stars in the night sky, all may depend on an ancient imbalance in which neutrinos or their hidden relatives played a part. There is also the question of whether neutrinos are their own antiparticles. Most particles have distinct antiparticles. The electron has the positron, a proton has an antiproton. But because neutrinos are neutral, it is possible in some theories that a neutrino and an antineutrino are not fundamentally separate in the same way. If this is true, it would have major implications for how neutrino masses arise and for the matter-antimatter story. Scientists search for a rare process called neutrinoless double beta decay, which would suggest that neutrinos are their own antiparticles. The process, if it exists, is extremely rare, so experiments need large detectors, quiet environments, and a great deal of patience. It is another case of listening for a whisper beneath a waterfall. Neutrinos also give us information from the cosmos. Solar neutrinos tell us about the processes inside the sun. Supernova neutrinos can escape from the collapsing core of a dying star before light fully breaks out, providing a direct message from one of the most extreme events in the universe. Neutrinos from distant astrophysical sources can travel across vast distances without being bent by magnetic fields, unlike charged cosmic rays. They may point back toward powerful cosmic accelerators, places where particles are hurled to enormous energies. In this way, neutrinos become messengers not only of particle physics but of astronomy. They connect the smallest known particles to the largest violent events in space. The fact that neutrinos can cross such distances with so little interference is both a blessing and a difficulty. It means they can bring clean information from places light struggles to reveal, but it also means they are extremely hard to catch. To detect them, we need enormous target volumes, sensitive instruments, and long periods of observation. The universe may be full of neutrinos, but almost all of them pass by without a trace. It is like standing in a rainstorm where the drops are so insubstantial that nearly everyone passes through your umbrella, your coat, and the street below without leaving anything wet. In the context of physics beyond the Standard Model, neutrinos are especially valuable because they are already known to be unusual. Unlike dark matter, whose particle identity remains completely unknown, neutrinos have been found and studied. They are real members of the particle family, but they do not sit comfortably in the simplest version of the theory. This makes them a proven crack in the old wall. Not a crack that destroys the building, but one that shows the wall is not the final boundary. Through it, we may glimpse hidden structures. Sterile neutrinos, if they exist, would widen that crack. They would suggest that the neutrino family extends beyond the three active types. They might explain mass patterns, contribute to dark matter, influence early universe history, or create signals in experiments that do not match the three neutrino framework. But their elusiveness also makes them difficult to confirm or rule out completely. Depending on their mass and mixing with ordinary neutrinos, they could hide in many ways. Some might be light enough to affect oscillation experiments, some might be heavy and appear only in rare particle decays or high-energy collisions. Some might be cosmologically important but almost impossible to produce in laboratories today. The phrase sterile shadow fits them well, not because it is mystical, but because their possible presence is inferred from how they might subtly alter the behaviour of the particles we can see. It is important to keep our balance here. Sterile neutrinos are not established particles, they are possibilities. Serious possibilities, but possibilities all the same. Physics does not accept a particle because it sounds useful. Many proposed particles sound useful, some sound almost too useful, like a universal remote left behind by nature. But a particle must be found through evidence. It must explain data better than alternatives. It must survive repeated tests. The history of neutrino physics teaches patience. The original neutrino itself took decades to confirm. The solar neutrino problem took decades to resolve. The current questions may take time too. Science moves slowly at the frontier because the frontier is where mistakes are easiest. Still, even without confirmed sterile neutrinos, the known neutrinos already tell us that the Standard Model is not the full story in its original form. Their masses require explanation. Their ordering is not fully known in every detail. Their exact absolute masses remain difficult to measure. Their possible role in the matter-antimatter imbalance is still being explored. Their nature as their own antiparticles or not remains unknown. These are missing pieces, and each piece may connect to physics at energy scales we cannot directly reach, or to particles too hidden for ordinary detectors. One of the most interesting things about neutrinos is how they turn absence into evidence. Missing energy led to their proposal. Missing solar neutrinos led to oscillations. Missing explanations for their mass lead to new theories. Missing interactions lead to the possibility of sterile states. Again and again, neutrinos appear where something does not quite add up. They are particles of the almost unseen, the nearly silent, the barely interacting. They remind us that the universe does not have to be loud to be important. And perhaps that is why they feel so appropriate for a calm journey through physics. Neutrinos do not crash into the story, they drift through it. They pass through stars, planets, detectors and bodies with an almost sleepy indifference. Yet they may carry information from the sun's core, from the death of stars, from the early universe, and from the hidden structure of particle laws. Their quietness is not emptiness, it is a different kind of presence. As we follow them, we begin to see how the search for particles beyond the standard model is not always a search for something huge and dramatic. Sometimes it is a search for the faintest change in identity, the smallest mass, the rarest decay, the almost impossible interaction. Sometimes the next clue does not roar from a collider. It arrives as a missing count in a detector, a subtle shift in a neutrino beam, or a signal so rare that years of silence must be understood before one event can speak. The known particles have already led us to dark matter, and neutrinos now lead us to hidden shadows of their own. But there is another idea that takes a different path. Instead of adding one quiet particle at a time, it imagines a deeper symmetry in nature, a hidden partner system in which every known particle may have a heavier counterpart. It is an idea built from elegance, problem-solving, and hope, and although experiments have not yet confirmed it, it remains one of the most famous attempts to look beyond the standard model. Supersymmetry begins with a tempting thought. What if the particles we know are only half of a larger family? What if every familiar particle in the standard model has a hidden partner, heavier, harder to produce and so far unseen? It is the sort of idea that feels almost too elegant, like opening a drawer and finding that every odd sock in the universe actually does have a match, just tucked away somewhere very inconvenient. For physicists, supersymmetry has been one of the most ambitious attempts to look beyond the known particle world. It does not simply propose one new particle to solve one problem. It suggests a whole hidden structure, a deeper pattern that could connect matter particles and force particles in a new way. To understand why that is interesting, it helps to remember that the particles we know are not all alike. In the standard model, matter particles such as quarks, electrons, muons, taus, and neutrinos belong to one broad class. Force-carrying particles such as photons and gluons belong to another. These classes behave differently at a deep quantum level. Matter particles have one kind of quantum character, while force particles have another. The difference is not merely cosmetic. It shapes how particles can occupy states, how they combine, and how the physical world is built. Matter particles make up the stuff of atoms. Force particles allow that stuff to interact. They are different roles in the same cosmic play. Supersymmetry asks whether those two roles might be connected by a deeper rule. In a supersymmetric theory, every matter particle would have a force-like partner, and every force-carrying particle would have a matter-like partner. The electron would have a heavier partner. Quarks would have heavier partners. The photon would have a partner. Gluons would have partners. Even the Higgs would sit inside a larger arrangement. These partner particles are not just copies with different hats. They would have related properties but a different quantum character. A particle from one class would be paired with a particle from the other. It is as if nature had written the known particle list in two columns, but we have only been able to read the first one. This is an appealing idea because symmetry has been one of the great guiding principles in physics. Symmetry does not always mean simple visual balance, like a butterfly wing or a neatly folded napkin. In physics, symmetry often means that something stays consistent when a transformation is made. Certain symmetries lead to conservation laws. Other symmetries shape the forces and particles themselves. The standard model is built on deep symmetry ideas, and those ideas have been extraordinarily successful. So when physicists found a possible new symmetry connecting matter and force particles, it was natural to take it seriously. Supersymmetry seemed like it might be more than a clever mathematical decoration. It might be a clue to a deeper layer of reality. One reason supersymmetry attracted so much attention is the Higgs boson. The Higgs field is central to the Standard Model because it helps explain why many particles have mass. But the Higgs also creates a puzzle. In certain calculations, the mass of the Higgs boson seems sensitive to very high energy effects. Without some kind of protection, one might expect it to be driven to values far larger than what experiments observe. The fact that the Higgs is relatively light compared with those enormous theoretical scales looks delicate. Some physicists call this a naturalness problem. That phrase can sound a little strange, as if the universe has been accused of wearing too much makeup. But in physics, it means that a measured value seems to require very precise balancing, unless there is a deeper reason behind it. Supersymmetry offered a beautiful possible reason. If every known particle has a partner, then the effects of ordinary particles and their supersymmetric partners could partly cancel in the calculations that affect the Higgs. The Higgs mass would be stabilised, not by an awkward fine-tuning but by a hidden symmetry. It would be like finding that a wobbly table does not stay upright because someone keeps adjusting it every morning, but because there is an unseen brace underneath. The brace may not be obvious from above, but it explains why the table is not falling over. For many physicists, supersymmetry felt like just such a brace under the Standard Model. This idea became even more attractive because supersymmetry could help with more than one problem. In many versions, the lightest supersymmetric particle would be stable. If it were neutral and weakly interacting, it could be a good dark matter candidate. That was a very exciting possibility. Dark matter needs some kind of particle identity if the particle interpretation is correct, and supersymmetry naturally seemed to provide one. Not as an extra patch added after the fact, but as part of a larger theory. The hidden partner family might include a particle that fills the invisible halos of galaxies. One idea could help explain the Higgs puzzle and dark matter at the same time. Physics does enjoy that sort of double usefulness. It is like discovering that the missing key also opens the cupboard where someone hid the biscuits. Supersymmetry also fits neatly into dreams of unification. In the Standard Model, the strengths of the electromagnetic, weak, and strong interactions change with energy. If you imagine running the theory backward toward the extreme energies of the early universe, the forces may come closer together. In some supersymmetric versions, the strengths appear to meet more elegantly, suggesting that the forces may have been unified at very high energies. This does not prove supersymmetry, but it adds to the sense that it may be pointing toward a deeper order. The known forces, so different in the present universe, might once have been aspects of a single interaction, later separating as the universe cooled. Supersymmetry seemed to make that old dream a little tidier. There is also a connection to string theory, where supersymmetry often appears naturally. String theory attempts to describe particles not as point-like objects, but as tiny vibrating strings, with different vibrations corresponding to different particles. Many versions of string theory rely on supersymmetry to be mathematically consistent. This made supersymmetry feel even more significant. It was not only a tool for particle physics, it seemed to belong to attempts at quantum gravity, to unification, to the deepest effort to make all forces part of a single framework. For a while, supersymmetry looked like a bridge between the Standard Model, dark matter, the Higgs puzzle, unification, and perhaps even gravity. That is quite a lot of responsibility for particles nobody has found yet. So where are these partner particles? That is the awkward question. If supersymmetry exists as a symmetry of nature, it cannot be an exact symmetry at the energies we normally observe. If it were exact, partner particles would have the same masses as known particles, and we would have found them long ago. There is no selectron sitting beside the electron with the same mass, no squark quietly joining the quark inside ordinary matter, no gluino casually wandering through detectors as if it belongs there. So if supersymmetry is real, it must be broken. The partner particles must be heavier than their known counterparts, perhaps much heavier. That would explain why they have not appeared in everyday matter or early low-energy experiments. This makes the search difficult. Heavy particles require high energy to produce. Particle accelerators are built in part to recreate conditions energetic enough for new particles to appear briefly. When particles collide at very high energies, some of that energy can become mass in the form of new particles if the laws of nature allow it. Supersymmetric particles, if they are within reach, might appear in the debris of these collisions. They would likely decay quickly into lighter particles, perhaps ending in a stable dark matter candidate that escapes the detector unseen. Physicists would look for patterns of visible particles plus missing energy, signs that something invisible had carried momentum away. For years, many hoped that the Large Hadron Collider would find supersymmetric particles. This was not a foolish hope. Some versions of supersymmetry suggested partner particles could appear near the energy range the collider was designed to explore. The discovery of the Higgs boson was a triumph, but the expected supersymmetric partners did not appear. Search after search placed stronger limits on their possible masses and interactions. Gluinos, quarks, leptons, neutrinos, charginos, and other possible superpartners were hunted in many channels. No confirmed signal emerged. The hidden family, if it exists, remained hidden. This has changed the mood around supersymmetry. Once, many physicists expected the simplest versions might show up relatively quickly. Now, those simplest versions are under pressure. The partner particles may be heavier than expected. The symmetry may be realized in a more complicated way. The signals may be harder to detect. Or supersymmetry may not be part of nature at accessible energies at all. Science does not promise that beautiful ideas are true. That is one of its great disciplines. A theory may be elegant, powerful, and deeply motivating, but experiments have the final say. Nature is not required to admire our taste, and yet supersymmetry has not simply vanished. Part of the reason is that it comes in many forms. The word supersymmetry describes a broad principle, not one single model. Some versions predict particles that should already have been seen, and are therefore strongly constrained. Other versions hide the particles more effectively, with heavier masses, compressed spectra, unusual decay chains, or weaker signals. Some versions are designed more for high-energy unification, or quantum gravity, than for immediate collider discovery. This flexibility is both a strength and a frustration. It keeps the idea alive, but it also makes it harder to test in one clean stroke. A very flexible theory can become like a cat at bedtime, always finding a new place to hide just when you thought you had located it. Still, the experimental limits matter. They force theorists to refine their models. They reduce the space of possibilities. They tell us which dreams were too simple. In that sense, even not finding supersymmetry is informative. It tells us that if nature is supersymmetric, the hidden family is not arranged in the most straightforward way many once expected. Perhaps the super partners are too heavy for current machines. Perhaps the connection to the Higgs is more subtle. Perhaps dark matter comes from another source. Or perhaps the whole idea, at least as a description of accessible particle physics, is not realized in our universe. These are all serious possibilities. The emotional story of supersymmetry is interesting because it shows how physics balances beauty and evidence. Supersymmetry is beautiful to many physicists because it relates particles that otherwise seem separate. It can soften the Higgs puzzle. It can provide dark matter candidates. It can improve unification. It appears in some deep mathematical frameworks. But beauty is not enough. The universe may be beautiful in ways we have not yet learned to recognize. A theory can feel like a perfect key and still fail to open the door. That does not make the search wasted. It teaches us about the lock. In a slower sense, supersymmetry also changes how we think about the known particle list. It invites us to imagine that the standard model is not merely incomplete by a few missing objects, but incomplete by structure. The particles we know might be one visible half of a larger arrangement. The familiar difference between matter particles and force particles might not be final. There might be a transformation that connects them, a hidden relation that ordinary energies conceal. This is a grand idea. Even if supersymmetry is not found soon, it has influenced the way generations of physicists think about what a deeper theory might look like. It asks us not only what particles exist, but what patterns connect them. The names of supersymmetric partners can sound a little playful, even though the theory is serious. The partner of an electron is often called a selectron. The partners of quarks are squarks. The partner of a gluon is a gluino. The partner of a photon is part of a more complicated mixture in realistic models, but names like photino appear in simple discussions. These names may make the hidden particle family sound like a whimsical copy of the known one, but the underlying idea is precise. For every known particle, a partner with related properties and different quantum behavior. A shadow list, not identical, but linked. If the lightest supersymmetric particle were stable, it might drift through the universe as dark matter. In many models, this candidate is called a neutrino, a mixture of partner states associated with neutral force and Higgs-related particles. A neutrino would not shine. It would not bind into atoms. It would pass through ordinary matter most of the time. It could have been produced in the early universe and survived to the present day, filling galactic halos. This idea once made supersymmetry one of the leading dark matter frameworks. Direct detection experiments, collider searches, and astronomical observations all tested pieces of this possibility. The lack of discovery so far has narrowed many versions, but the general dark matter motivation remains historically important. There are other possible supersymmetric dark matter candidates too, depending on the model. The details can become technical, and for our quiet journey we do not need to wander too far into that thicket. The important point is that supersymmetry naturally created new stable or long-lived particles that could behave like dark matter. It made the dark universe feel connected to a deeper symmetry rather than an isolated mystery. That kind of connection is very appealing. Physics often advances when separate puzzles turn out to be different faces of one underlying idea. Electricity and magnetism became electromagnetism. Space and time became space-time. Maybe dark matter and the Higgs puzzle might have shared a supersymmetric explanation. Maybe they still might, though not in the simplest way once hoped. One should not imagine that experiments search for supersymmetry only by looking for one obvious particle bump. The searches are varied and subtle. Some look for jets of particles plus missing energy. Some look for leptons and missing energy. Some look for long-lived particles that travel a measurable distance before decaying. Some look for unusual tracks, displaced vertices, or rare processes. Some search for heavy partners of strongly interacting particles, which would be produced more often if light enough. Others search for electro-weak partners, which may be harder to produce and easier to miss. The detector is like a huge listening device, and supersymmetry could sing in many different registers. So far, none of those songs has been clearly heard. The absence of a signal at current colliders has led to broader reflection. Maybe the naturalness problem is not solved by new particles near the energy scale we expected. Maybe our sense of what counts as natural needs revision. Maybe the Higgs mass is the result of environmental selection in a larger landscape of possible universes. Maybe another mechanism stabilizes it. Maybe future colliders will reveal particles just beyond our reach. This is where the frontier becomes philosophical as well as technical, though still grounded in experiments. When nature does not behave according to our expectations, we must decide whether the expectations were wrong, the searches were incomplete, or the signal is simply farther away. There is something deeply human in that. We love patterns, we are drawn to symmetry. We expect hidden order behind visible complexity. Often that instinct has served science well. Other times, nature has chosen a messier path. Supersymmetry sits right at that tension. It is an elegant hidden order that may or may not be realized in the world we can test. It is not a fantasy because it has clear mathematical structure and experimental consequences. But it is not established fact because the particles have not been found. It lives in the disciplined middle ground of theoretical possibility, constrained by data still watched carefully. If supersymmetric particles are discovered one day, the effect would be enormous. It would instantly show that the known particle world is part of a larger structure. It could provide a dark matter candidate. It could reshape our understanding of the early universe. It might point toward unification and deeper theories including gravity. A single confirmed superpartner would open a door to an entire hidden family. The standard model would not be destroyed. It would be expanded, placed inside a richer framework. The tiny rulebook would become the visible chapter of a larger manual, though we should not use that word too loudly since this is supposed to stay restful. If supersymmetry is never found, it will still have taught physics something. It has sharpened questions about the Higgs, dark matter, unification and naturalness. It has guided experiments to search in many clever ways. It has helped develop mathematical tools and theoretical insights used across particle physics. Even wrong ideas can be useful if they are precise enough to be tested. The worst ideas are not the ones that fail. The worst are the ones that can never be clearly checked. Supersymmetry, for all its flexibility, has repeatedly met the pressure of experiment. That is why it remains part of the serious conversation. The dream of a hidden particle family is therefore both hopeful and humbling. Hopeful because it suggests that the universe may have a deeper symmetry beneath the apparent clutter of particle masses and forces. Humbling because decades of searching have not yet revealed it. The hidden family, if real, is not waiting just under the doormat. It may be locked away at higher energies, disguised in subtle signals or absent entirely. The universe has allowed us to imagine it, but not yet to claim it. As we rest with this idea, it is useful to return to the broader search beyond the standard model. Supersymmetry is one grand possibility, but it is not the only one. The missing pieces may not arrive as a full mirrored family. They may come as a single quiet particle, an axion born from a puzzle in the strong force, or a dark matter candidate that barely touches ordinary matter, or a weakly interacting particle that once seemed like the most natural suspect in the cosmic dark. The search continues along many paths at once, because the universe has given us more than one mystery, and no guarantee that all of them share the same answer. The search for particles beyond the standard model often feels like listening in the dark. We know something is there, or at least something seems to be there, because gravity keeps pointing toward it. Galaxies turn too quickly. Galaxy clusters hold together too strongly. Light bends around invisible mass. The early universe grew structure in a way that makes far more sense if unseen matter was already helping the visible matter gather. And yet, when we ask what that unseen matter is made of, the answer remains just out of reach. It may be a particle. It may be more than one particle. It may be part of a hidden sector with its own rules, or it may force us to rethink something deeper. But among all the possible answers, a few names return again and again like quiet footsteps in a long hallway. Axions, weakly interacting massive particles, dark photons, hidden neutrinos, particles so faintly connected to ordinary matter that we have not caught them yet, but not so impossible that the search becomes hopeless. The phrase ghosts in the dark is not a scientific category, of course. It is just a useful way to picture the problem. These proposed particles are not ghosts in the supernatural sense. They are not spirits drifting through old houses, making floorboards creak at midnight, though that would certainly make the detector results more interesting. They are ghostly because they may pass through ordinary matter almost unnoticed. They may fill space without shining. They may move through planets, stars and laboratories with only the faintest chance of leaving a mark. They may be abundant and important while remaining nearly invisible to the instruments we use to study the world. That combination is both frustrating and fascinating. It means the universe might be full of something that is not absent, only quiet. For many years, one of the most famous dark matter candidates was the weakly interacting massive particle. The idea was appealing because it seemed to arise naturally in several theories beyond the standard model. Such a particle would have mass, would not carry electric charge, and would interact with ordinary matter only rarely, perhaps through the weak nuclear force or something similarly faint. It would not emit light, it would not form atoms, it would not clump into glowing stars, but it could still have gravity, and if enough of it existed, it could shape galaxies. A particle like this could have been produced in the early universe and survived to the present day, drifting through cosmic halos around galaxies like a dark, invisible mist. The attraction of weakly interacting massive particles came partly from what is sometimes called a coincidence, though physicists are cautious with that word. In simple versions, a particle with roughly the right mass and interaction strength could naturally freeze out of the hot early universe, with an abundance similar to what dark matter appears to have today. That means the early universe would produce many of these particles, and as the universe expanded and cooled, their interactions would become less frequent until a leftover population remained. This leftover population could then be the dark matter we observe through gravity. It was a neat story, a little too neat perhaps, but neatness is not a crime in physics. It only becomes suspicious when nature refuses to cooperate. To find weakly interacting massive particles, scientists built experiments deep underground. These detectors are placed beneath rock because the surface of Earth is constantly struck by cosmic rays, which create background signals. If you're trying to hear a whisper, you do not stand beside a busy road. You go somewhere quiet. Underground laboratories are among the quietest places scientists can build for this purpose, though quiet here means quiet in particle terms. There is still radioactivity from materials, still neutrinos passing through, still tiny unwanted signals that must be understood and reduced. The detector materials must be pure, the shielding must be careful, the analysis must be patient. The hope is that a dark matter particle will occasionally strike an atomic nucleus, producing a tiny flash vibration or charge signal that can be recorded. There is something almost meditative about this kind of search. A large tank of liquid xenon, for example, may sit deep underground, watched by sensitive instruments, waiting for an event so rare that it may not happen for a long time. The experiment does not chase the particle, it waits, it removes noise, it learns its backgrounds, it asks matter to sit very still and notice the faintest touch from the dark. If the signal appears, it must match the expected pattern. If it does not appear, that absence also teaches something. It says that certain kinds of weakly interacting massive particles cannot be as common or as strongly interacting as once hoped. Slowly, carefully, the possible hiding places shrink. Collider experiments look for these particles in a different way. If high-energy collisions can create dark matter particles, the particles may escape the detector without interacting. The detector would then record an imbalance, as if visible energy and momentum did not quite add up. Something unseen may have carried part of it away. Of course, missing energy is not automatically dark matter. Neutrinos also escape detectors and create missing energy, and many ordinary processes can imitate new physics if not understood properly. The art is in comparing the data to the standard model with great precision. A real dark matter signal would need to stand out from the known backgrounds, not just as a strange event, but as a repeated and statistically convincing pattern. Astronomers also search for signs of weakly interacting massive particles in the sky. If dark matter particles can collide with each other and annihilate, they might produce ordinary particles, gamma rays, or other signals. Regions with high dark matter density, such as the centers of galaxies or certain small satellite galaxies, become places to look. But again, the universe is noisy. Stars, pulsars, black holes, supernova remnants, and cosmic ray interactions can produce energetic radiation. A possible excess may look intriguing for years and then become less mysterious when a better astrophysical explanation appears. This is not discouraging. It is how science avoids fooling itself. The dark does not get to claim every unexplained glow. Despite decades of searching, weakly interacting massive particles have not been confirmed. That does not prove they do not exist, but it has changed expectations. Many simple versions are now strongly constrained. If these particles are real, they may interact even more weakly than first thought, have masses outside the easier search ranges, or belong to more complicated dark sectors. The search continues, but the once comfortable pictures become less certain. This is a familiar pattern in physics. A beautiful candidate steps forward, makes several excellent arguments, and then experiments politely ask for identification. So far, the identification has not been provided. Axions offer a very different kind of possibility. They are not heavy dark matter candidates in the same style as weakly interacting massive particles. They were originally proposed to solve a problem in the strong nuclear force, a subtle issue involving why certain symmetries appear to be respected much more than one might expect. The details are technical, but the essential idea is that introducing a new field and a new particle, the axion, could naturally explain why the strong force behaves in this surprisingly balanced way. What makes the axion especially interesting is that this particle, proposed for one reason, could also be dark matter. Sometimes physics gives you a tool that might open more than one locked door. Naturally, this makes everyone very attentive to where the tool has gone. If axions exist, they are expected to be extremely light and very weakly interacting. They would not behave like ordinary particles bouncing around in a detector very often. Instead, dark matter axions might form a coherent field spread through space, more like a faint background hum than a rain of heavy grains. This changes the experimental approach. Some axion searches use powerful magnetic fields, because under the right conditions an axion could convert into a photon. The experiment then tries to detect those photons. But the expected signal depends on the axion mass, which is not known. So the search often involves tuning an instrument across possible frequencies, listening for a tiny excess, like slowly turning the dial on an old radio, and hoping to catch a station broadcasting from the hidden side of the universe. That radio image is not perfect, but it is useful. Axion detectors are not listening to sound, and the universe is not playing jazz in a basement somewhere, though at times one wonders. They are looking for a very specific conversion signal, guided by theory and constrained by noise. The challenge is enormous because the coupling between axions and ordinary matter may be extremely weak. The signal may be tiny, the equipment must be sensitive, the environment must be controlled, but the reward would be profound. Finding an axion could solve a deep problem in particle physics and identify the dark matter at the same time. It would show that a quiet idea from the theory of the strong force also fills the halos of galaxies. That would be an elegant twist, and physics does enjoy a twist when it is backed by data. Axions also come in related forms. Some theories propose axion-like particles, which share certain features with axions but are not tied to the same original problem. These particles could have different masses and interactions. They might arise in broader theories beyond the standard model, including some inspired by attempts to unify forces or include gravity. The family of axion-like possibilities is large, and experiments search across many ranges. Some look in laboratories, some use astrophysical observations, some study how these particles might affect stars, black holes, or light travelling across cosmic distances. As with many hidden particle searches, the difficulty is that a particle with weak enough interactions can hide almost anywhere. The trick is finding the places where even faint interactions become visible. Then there are dark photons. The ordinary photon carries electromagnetism, which is why light, electricity, and magnetism are connected. A dark photon would be a hypothetical force carrier for a hidden electromagnetic-like force, one that acts mostly on dark sector particles rather than on ordinary matter. It might mix very slightly with the ordinary photon, allowing a tiny connection between the dark sector and our visible world. This idea is attractive because it gives dark matter or hidden particles a possible internal force of their own. Dark matter does not have to be a single lonely particle species doing nothing but gravitating. It might belong to a hidden world with its own interactions, though those interactions may be mostly invisible to us. A hidden sector does not mean there is a shadow version of everything we know. That is a tempting science fiction image, but the serious models are usually much more restrained. A hidden sector might contain one or several particles, a new force, or a small set of interactions that communicate weakly with the standard model through what physicists call portals. A portal is not a glowing doorway in space, sadly. It is a possible connection between known fields and hidden fields. The Higgs could be one portal, neutrinos could be another, the photon could mix with a dark photon. These are ways hidden particles might influence ordinary matter just enough for us to detect them, while remaining mostly separate. This idea expands the dark matter question. Instead of asking only which single particle makes up dark matter, physicists can ask whether dark matter has structure. Could there be more than one dark particle? Could dark matter interact with itself? Could those interactions solve puzzles about galaxy formation or the distribution of matter in small galaxies? In some models, dark matter is not entirely collisionless. It may have self-interactions that alter how it clusters in the centers of galaxies. These ideas are tested through astrophysical observations, simulations, and laboratory constraints. The dark universe may be simple, but it may also be more interesting than a single silent particle. Sterile neutrinos, which we met earlier, also belong in this gallery of dark possibilities. A sterile neutrino with the right properties could act as dark matter. It would be lighter than the classic weakly interacting massive particle, and would interact mainly through its faint mixing with ordinary neutrinos. Such a particle might decay extremely rarely, perhaps producing faint X-ray signals that astronomers could search for. There have been tentative hints in the past, debated and examined with great care, but no confirmed discovery. Sterile neutrino dark matter remains possible in some forms, constrained in others, and surrounded by the usual fog that comes with particles that barely interact. Primordial black holes sometimes enter the dark matter conversation too, although they are not particles beyond the standard model. They would be black holes formed in the early universe, perhaps from dense regions shortly after the Big Bang. If enough of them existed in the right mass ranges, they could contribute to dark matter. This idea is different because it does not introduce a new particle. It asks whether dark matter could be made of compact gravitational objects instead. Observations have ruled out many ranges and limited how much primordial black holes can contribute in many scenarios, but some windows remain discussed. Their inclusion reminds us that dark matter is a problem with several possible kinds of answers, not all of them particle-based. Still, the particle route remains one of the most active because it connects so naturally with the unfinished business of the standard model. The variety of candidates can feel overwhelming. Weakly interacting massive particles, axions, axion-like particles, dark photons, sterile neutrinos, hidden sector states, self-interacting dark matter, primordial black holes. It is like arriving at a very strange job interview where every candidate claims to be invisible, rarely speaks, and may or may not have shaped the evolution of galaxies. How does one choose? The answer is evidence. Each candidate makes predictions, sometimes direct, sometimes subtle. It may predict a scattering signal in underground detectors. It may predict a photon conversion in a magnetic field. It may predict missing energy at colliders. It may predict a line in cosmic radiation, a change in galaxy structure, a shift in early universe patterns, or a rare decay. Scientists do not choose the most charming candidate. They follow the clues. What makes dark matter especially challenging is that several candidates can explain the broad gravitational evidence. Gravity tells us that something is there, but gravity alone does not reveal the particle identity. It tells us about mass and distribution, not about charge, spin, interactions, or origin. That is why multiple kinds of experiments are needed. Cosmology maps the large-scale behaviour. Astronomy studies galaxies and clusters. Underground detectors search for rare collisions. Colliders try to produce new particles. Precision experiments look for tiny effects. No single method is enough. The identity of dark matter, if it is a particle, may require several clues to line up at once. There is a gentle lesson here about how science handles the unseen. It does not simply believe in invisible things because they are convenient. It builds a case from effects. The atom was once unseen. The neutrino was once only an explanation for missing energy. The Higgs boson was once a predicted ripple in a field not directly observed. In each case, the unseen became accepted because the evidence became strong enough and specific enough. Dark matter has strong evidence as a gravitational phenomenon. The next step is to identify what it is. That is the harder part. It is one thing to know someone is moving around upstairs because the floorboards creak. It is another to know their name, height, favourite snack, and whether they are wearing slippers. Axions and weakly interacting massive particles represent two different moods in the search. The weakly interacting massive particle is the heavier, more collision-based suspect, once expected to show itself through rare bumps in detectors or missing energy at colliders. The axion is lighter, quieter, more field-like, requiring experiments that tune and listen for delicate conversions. Dark photons and hidden sectors suggest that the dark world may have its own forces. Sterile neutrinos connect the dark matter question to the already strange behaviour of known neutrinos. Each path has its own instruments, its own expectations, and its own frustrations. Together they show how rich the search has become. As experiments become more sensitive, they also begin to encounter new limits from known particles. Neutrinos, for example, create a background for some dark matter searches. There is a point where detectors become so sensitive that neutrinos from the sun, atmosphere, and other sources can mimic some of the signals expected from dark matter. This is sometimes called a neutrino flaw, though it is not an absolute flaw in every sense. It means the search becomes harder, requiring more information about direction, timing, or signal type to distinguish dark matter from neutrinos. There is a certain humour in this. The particle once famous for being nearly impossible to detect becomes, for we dark matter hunters, part of the background noise. Even ghosts can get in each other's way. The absence of discovery so far has not made the search less important. It has made it more focused. Each null result removes some possibilities. Each new detector explores a different range. Each astrophysical observation tests another prediction. The dark matter problem is too well supported to ignore, and the standard model still lacks a particle that can solve it. Somewhere in the space of possibilities there may be a new particle waiting to be found, or a new lesson waiting to tell us that our assumptions were too narrow. Either way, the search is teaching us how to ask better questions. It is also worth remembering that the universe does not owe us a simple dark matter particle. Dark matter could be made of more than one component. It could include axions and something else. It could involve a hidden sector with stable and unstable particles. It could behave differently in different cosmic settings. Or it could be something we have not yet imagined clearly. The names we use now may one day seem like early guesses, useful stepping stones toward a better idea. That is not a weakness. It is how frontier science looks from the inside. The map is incomplete, but the compass is working. For a quiet mind, there is something almost comforting in the thought that the universe still has hidden ingredients. Not because ignorance is comforting, but because discovery remains possible. The night sky is not just a picture of what we know. It is also a record of what we have not yet understood. The galaxies are bright, but their motions trace darkness. The detectors are silent, but their silence has meaning. The theories are many, but each one is a careful attempt to name the invisible. So the ghosts in the dark are not fantasies. They are candidates born from real problems, shaped by mathematics, and tested by machines built with extraordinary care. Some may vanish as experiments improve. Some may survive. One may eventually step out of the darkness through a tiny flash in a detector, a narrow signal in a magnetic field, a missing energy pattern in a collider, or a faint clue from the sky. And that brings us naturally to the tools of the search itself, the machines, observatories, underground chambers, and cosmic messengers that scientists use when they try to catch what barely interacts, measure what does not shine, and ask the dark universe what it is made of. The search for new particles is not a single hunt with one net, one telescope, or one enormous machine humming under the countryside. It is more like listening for a faint sound with many different kinds of ears. Some instruments listen underground, hidden beneath rock, waiting for rare touches from particles that may pass through almost everything. Some listen in the sky, watching light, cosmic rays, neutrinos, and distant explosions for clues written across space. Some create violent collisions in laboratories, briefly concentrating energy into tiny regions, hoping the universe will reveal particles that ordinary conditions cannot produce. Each method asks the same quiet question in a different language. Is there something beyond the particles we already know? Particle colliders are perhaps the most dramatic of these tools. They are the great engines of experimental particle physics, built to make the smallest things visible through the largest machines humans can construct. The basic idea is simple enough in spirit. Take particles, accelerate them to extremely high speeds, guide them around with powerful magnets or along long paths, then smash them together and study what comes out. It sounds almost childishly direct, like a very expensive version of crashing toy cars to see where the wheels go. But beneath that simple image is some of the most precise engineering and analysis ever attempted. When particles collide at high energy, the collision is not just a messy breakage, it is an opportunity. Energy can become new particles, including particles heavier than the ones that entered the collision, if the conditions are right and the laws of physics allow it. Many unstable particles cannot be found sitting around in ordinary matter because they decay far too quickly. But in a collider, they may appear for a tiny fraction of a moment and then decay into other particles that detectors can record. Physicists do not usually see the new particle directly. They see its traces, its decay products, the pattern it leaves in the debris. The particle is known by its consequences, like a guest who leaves before you enter the room but forgets a very unusual hat on the chair. The detectors around collider collision points are enormous and layered. They are designed almost like onion skins of measurement. Near the centre, tracking systems follow the paths of charged particles. Other layers measure energy deposited by particles. Some parts identify muons, which can pass through much of the detector before being caught. Magnets bend charged particles, revealing their momentum and charge. The whole machine is built to reconstruct what happened in the collision from the spray of outgoing particles. A single event can contain many tracks, showers and signals. It is not a tidy picture. It is more like a firework exploding inside a cathedral-sized camera that must decide calmly and very quickly which sparks matter. The amount of data produced is enormous. Most collisions are not interesting in the sense of revealing new physics. They are known processes happening again and again, important for calibration and comparison, but not the rare signal everyone hopes for. The challenge is to find the unusual event hidden inside an ocean of ordinary ones. A new particle might appear only once in billions of collisions. It might decay in a way that resembles known processes. It might produce missing energy by escaping the detector, or it might leave a displaced track if it lives slightly longer than expected before decaying. It might be heavy and rare, or light and subtle. It might be obvious in hindsight and nearly invisible before discovery. This is why collider physics requires both powerful machines and extraordinary patience. The discovery of the Higgs boson is a classic example of how such a search works. The Higgs did not appear as a little glowing dot labelled with its own name. It decayed into other particles, and those decay patterns had to be extracted from background processes. Scientists looked for a statistically significant excess, a pattern appearing where the theory predicted it should if the Higgs existed. The discovery was not one collision saying hello. It was many events, carefully combined, rising above the noise. That is often how new physics must announce itself. Not as a shout, but as a repeated whisper that refuses to go away. When colliders search beyond the standard model, they look for several kinds of clues. One clue is a resonance, a bump in the distribution of collision products. If a new particle is produced and decays into known particles, the combined energy of those decay products can reveal the particle's mass as a peak above the expected background. This is rather like hearing many notes in a noisy room, and noticing that one pitch keeps appearing more often than chance would allow. Another clue is missing energy, suggesting that invisible particles escape the detector. Neutrinos already do this, so the known background must be understood carefully. But if the missing energy appears with certain patterns, it might suggest dark matter particles or other hidden states. Physicists also look for rare decays. Some particles are produced in large numbers, and their decays are predicted very precisely by the standard model. If a decay happens more often than expected, less often than expected, or in a pattern that looks slightly wrong, it could point toward new particles influencing the process indirectly. This is an important point. A new particle does not always have to be produced directly to be discovered. Sometimes it can affect known processes through subtle quantum effects. The particle is like someone behind a curtain pulling lightly on a string. You do not see the person, but the curtain moves in a way that tells you someone may be there. This indirect approach can reach particles too heavy to produce directly, if their influence on known particles is strong enough. Precision becomes a kind of telescope. The more accurately you can measure something, the more sensitive you become to tiny deviations. A particle beyond the standard model might show itself not through a spectacular burst, but through a small disagreement between prediction and measurement. The difficulty, of course, is that both theory and experiment must be extremely well understood. A tiny mismatch could be new physics, or it could be an overlooked background, a detector effect, a calculation issue, or plain statistical fluctuation. Physics at the frontier requires a very steady temperament. One must be excited by hints, but not seduced by them too quickly. There have been many hints over the years. Some have faded, some remain under study. This is normal. The search for new physics is full of almost discoveries. An anomaly appears in one experiment, becomes exciting, then weakens as more data arrives. A tension shows up between measurements, then turns out to depend on a difficult background. A possible excess survives for a while, then another experiment does not confirm it. This can feel disappointing from the outside, but it is not wasted effort. Every hint teaches scientists where the theory is strong, where the instruments need refinement, and where nature is not hiding. The path to discovery is often paved with careful non-discoveries. Colliders are not the only way to search. Nature itself creates particle collisions far more energetic than many laboratories can manage. Cosmic rays, high-energy particles from space, strike Earth's atmosphere constantly. Most are protons or atomic nuclei travelling at great speeds. When they hit atoms in the upper atmosphere, they create showers of secondary particles that rain down through the air. Some of these particles reach the ground. Some can be detected by instruments spread over large areas. Cosmic rays are like messages from powerful astrophysical engines, though the messages arrive scrambled by magnetic fields and transformed by atmospheric collisions. The origins of the highest energy cosmic rays remain a major area of study. They may come from active galaxies, exploding stars, extreme magnetic environments, or other powerful cosmic accelerators. Because charged cosmic rays are bent by magnetic fields on their journey, it can be difficult to trace them back to their sources. They do not travel in straight lines like photons or neutrinos. They wander, curve, and arrive like guests who took a very complicated route and refuse to explain where they started. Still, their energies tell us that the universe can accelerate particles in ways that are astonishing. By studying them, scientists learn about both astrophysics and high-energy particle behavior. Cosmic rays can also search for new physics indirectly. If dark matter particles annihilate or decay, they might produce excesses in cosmic ray particles, such as positrons or antiprotons. Detectors in space and on Earth look for unusual patterns in these particles, but again, the challenge is interpretation. Pulsars and other astrophysical sources can produce similar signals. Cosmic ray propagation through the galaxy is complex. The galaxy is not a clean laboratory where conditions can be controlled. It is more like a kitchen after a large family dinner, with many things happening at once and nobody entirely sure who spilled what. A strange cosmic ray signal may be dark matter, but it may also be an ordinary astrophysical source wearing a mysterious coat. Neutrino observatories add another window. High-energy neutrinos can travel across the universe without being deflected by magnetic fields and without being absorbed easily by matter or light. They may point back more directly to their sources. Giant detectors embedded in ice or water watch for the rare interactions of these neutrinos. A single high-energy cosmic neutrino can carry information about violent processes far away. Some may come from active galactic nuclei, gamma-ray bursts, starburst galaxies, or other extreme environments. If unexpected neutrino patterns appear, they could reveal new astrophysics or even new particle behavior. Neutrinos are difficult messengers, but they are unusually honest about direction. Gamma-ray telescopes also search the sky for signs of new physics. Gamma rays are very energetic light, and they can come from many sources, including pulsars, black holes, supernova remnants, and cosmic ray interactions. If dark matter annihilates or decays, it might also produce gamma rays. Scientists look at regions where dark matter should be abundant, such as the centre of our galaxy or nearby dwarf galaxies. Dwarf galaxies are especially useful because they may contain a lot of dark matter and relatively little ordinary astrophysical clutter. They are quiet neighbourhoods compared with the busy galactic centre. If a gamma-ray signal appeared from several dark matter-dominated dwarf galaxies with the right pattern, it would be very interesting. So far, no confirmed dark matter signal has emerged, but the searches continue to narrow the possibilities. There are also experiments that look for rare events in ordinary matter. Proton decay is one example from theories that attempt to unify forces. In some grand unified theories, the proton is not perfectly stable, only incredibly long-lived. If protons can decay, then huge detectors containing enormous numbers of protons might eventually catch one doing so. No proton decay has been confirmed, and the proton's lifetime, if finite, must be extraordinarily long. But the search is meaningful because one confirmed decay would reveal physics far beyond the standard model. It would suggest that quarks and leptons are connected in a deeper way, and that the forces may unify at high energies. A single proton quietly transforming would be a message from an energy scale far beyond what colliders can directly reach. Precision experiments form another part of the search. These do not always look as dramatic as giant colliders, but they can be just as powerful. Scientists measure properties of known particles with extreme accuracy. They study magnetic moments, electric dipole moments, rare transitions, atomic clocks, and subtle symmetry violations. A tiny deviation from the standard model prediction might indicate the influence of unknown particles. In this kind of experiment, the laboratory may look quieter, but the sensitivity is extraordinary. It is like trying to detect the weight of a feather by watching how a mountain shifts. Difficult, yes, but not impossible if the instrument is clever enough. One famous kind of precision search involves looking for electric dipole moments of particles such as the neutron or electron. An electric dipole moment would indicate a separation of charge within a particle, and could reveal new sources of matter-antimatter asymmetry. The standard model predicts extremely tiny effects in many cases, so a larger measurement would be strong evidence for new physics. These experiments are hard because the expected signals are so small. They require careful control of magnetic fields, electric fields, temperature, motion, and environmental noise. The reward would be enormous. A non-zero signal at the right level could point toward the kind of new interactions needed to explain why matter survived in the early universe. Another frontier involves flavor physics, the study of how different types of quarks and leptons behave and transform. The standard model has precise rules for these processes, and some rare decays are especially sensitive to new particles. Experiments studying heavy particles containing bottom quarks, charm quarks, or tau leptons can test whether the known pattern holds. If certain decays occur differently than expected, new particles may be influencing them indirectly. This is a subtle search, less famous than smashing protons at the highest possible energies, but extremely important. Sometimes the shortest route to new physics is not brute force, but careful listening to rare behaviour. Astrophysics and cosmology also act as enormous laboratories. The early universe reached energies and densities far beyond anything humans can recreate. Its leftover patterns are recorded in the distribution of galaxies, the abundance of light elements, the cosmic background radiation, and the growth of structure. New particles could have affected any of these. Extra light particles in the early universe might change the expansion rate. Dark matter properties shape how galaxies form. Interactions between dark matter and ordinary matter could leave marks on cosmic structure. Particles involved in inflation, if inflation occurred, could leave patterns in the primordial universe. Cosmology does not let us repeat the experiment, which is inconvenient, but it gives us the result of an experiment the universe already performed. In this sense, the universe itself is the largest collider. The Big Bang was not a collider in the ordinary laboratory meaning, but the early universe explored extreme conditions. If new particles existed then, they may have influenced what came later, even if they are now too rare, too heavy, or too hidden to produce directly. We search for their footprints in the cosmic record. The challenge is that cosmological clues often depend on models and many connected assumptions. But when laboratory physics, astrophysics, and cosmology all point in the same direction, the case can become powerful. The search for new physics is therefore wide and layered. Colliders create particles directly if they can. Underground detectors wait for dark matter to touch ordinary matter. Telescopes look for radiation from hidden processes. Neutrino observatories listen for nearly invisible messengers. Precision experiments measure known particles so carefully that unseen ones may reveal themselves through tiny shifts. Cosmic surveys map the structure of the universe. No single approach is guaranteed, but together they form a net cast across many scales, from the smallest measured properties of particles to the largest patterns of galaxies. There is also a practical reason to use many methods. New particles can hide in different ways. A particle too heavy for a collider might still affect precision measurements. A particle too weakly interacting for direct detection might appear through astrophysical decay. A particle that leaves no clear sky signal might still be produced in a collision. A particle connected to neutrino mass might show itself in rare decays rather than dark matter experiments. The universe has many pockets. Scientists must check as many as possible, while trying not to mistake lint for treasure. It is worth appreciating the human side of this search. These experiments take years, sometimes decades. They involve thousands of people, enormous collaborations, long nights of calibration, careful debates, software, engineering, statistics, and patience. A detector must be built before it can listen. A collider must be maintained before it can collide. A telescope must be understood before it can interpret the sky. Discovery, when it comes, may look sudden in a headline, but underneath it are years of quiet labour. New physics does not usually arrive like lightning on a clear day. It arrives after many people have spent a long time making sure the clouds are real. And the search can be emotionally strange. Physicists often build experiments hoping to find something that might not be there. They design instruments sensitive enough to test a theory, knowing the result may be silence. But silence is still a result. If an experiment finds no dark matter interaction, it tells us that dark matter, if it exists in that form, must interact more weakly or have different properties. If a collider finds no supersymmetric particles in a certain range, it reshapes the theory landscape. If precision measurements agree with the standard model yet again, they make any new physics more constrained and perhaps more subtle. The universe can answer no in very informative ways. There is a calm beauty in that. Science is not only the celebration of yes, it is the careful understanding of no. No signal here. No particle at this mass, no decay at this rate, no deviation within this uncertainty. These are not empty statements. They are walls on the map. They guide the next search. They prevent imagination from drifting too far without evidence. They help turn mystery into a more precise shape. Still, the hope remains. Somewhere there may be a signal that does not fade, a collision pattern that repeats. A dark matter event that matches direction, timing and energy. A rare decay that cannot be explained away. A cosmic ray pattern pointing to an unexpected source. A neutrino behaviour that requires a hidden state. A precision measurement that disagrees with the standard model in exactly the way a new theory predicts. It may come from a giant collider, or from a quiet underground chamber, or from a telescope watching a faint dwarf galaxy, or from an experiment so precise it seems almost absurd. New physics could arrive through the grand or the delicate. The important thing is that the search is not random. It is guided by the gaps we have already met. Dark matter gives one target. Neutrino mass gives another. The matter-antimatter imbalance gives another. The Higgs puzzle gives another. Gravity and quantum theory give another. The patterns of particle generations, force strengths and rare decays give still more. Each gap suggests certain experiments, and each experiment tests certain possibilities. The unknown is large, but not shapeless. As we follow these searches, we begin to see the frontier of physics not as a single locked door, but as a long corridor of carefully marked doors. Some lead to empty rooms, some are still closed. Some may open onto ideas we have not yet named. The standard model stands behind us, sturdy and successful. The instruments stand before us, listening in different ways. And beyond them, if nature has chosen to place them there, may be particles that explain dark matter, reveal hidden symmetries, connect forces, or show why the universe became rich with matter instead of fading into pure radiation. For now, the machines keep running, the detectors keep waiting, and the telescopes keep watching. Cosmic rays strike the atmosphere. Neutrinos pass through the planet. Protons collide in tunnels. Atoms sit in quiet chambers waiting for rare touches. The sky continues to carry messages from violent places, and the early universe continues to leave its faint handwriting across the cosmos. Every method has limits, but together they form one of the most patient questions humanity has ever asked. If there are particles beyond the standard model, where are they hiding, and what will they reveal when they are finally found? If particles beyond the standard model are ever found, they will not simply add a few new names to a chart. They may change the way we understand matter, space, time, the early universe, and perhaps even why there is anything here at all. That is why this search matters so much. It is not just a collector's hunt for rare pieces, like someone trying to complete a set of cosmic trading cards. It is an attempt to learn whether the familiar world is only the visible part of a deeper order. The known particles already build atoms, light, chemistry, stars, and bodies. They explain so much that it is easy to feel, for a moment, that the small ingredients of reality have been fully counted. but the universe keeps leaving evidence that the count is not finished. A new particle could reveal the identity of dark matter. That alone would be one of the greatest discoveries in modern science. Right now, dark matter is known mostly through gravity. It shapes galaxies, bends light, guides the growth of cosmic structure, and seems to outweigh ordinary matter by a large amount. Yet we do not know what it is. If a dark matter particle were detected in an underground experiment, a collider, a telescope signal, or some other clever method, the invisible scaffolding of the universe would suddenly become part of particle physics. We would move from saying something unseen is there to saying this is what it is. That would be a huge change. The dark halos around galaxies would no longer be only gravitational maps. They would be made of a known ingredient, a particle with mass, behaviour, history, and a place in the larger story. Think of how strange that would be. Every galaxy, including our own Milky Way, appears to be embedded in a vast dark halo. If dark matter is a particle, then Earth is moving through that halo right now. You're moving through it too, quietly, constantly, without feeling it. The room around you may be crossed by dark matter particles every moment, passing through walls, furniture, skin, bone, and air without noticing much at all. If we identified those particles, the space around us would feel different in the imagination. Not empty, not merely filled with air and light and radio waves, but also with a hidden population that has been here all along. It would be like discovering that a silent ocean had been flowing through every room of every house on Earth, not metaphorically, but physically, in the deep language of particles. A new particle might also explain why neutrinos have mass. Neutrinos are already known to be unusual, and their tiny masses are one of the strongest signs that the standard model, in its original form, cannot be the whole story. If hidden neutrino-related particles were found, perhaps sterile neutrinos or heavier states connected to the early universe, they could reveal how neutrino masses arise. They might show that the neutrino sector is a doorway into a much larger hidden structure. That would be a quiet kind of revolution, not necessarily as visually dramatic as a bright new collider signal, but just as profound. The least interactive known matter particles may turn out to be the ones that knew where the next door was. There is also the matter-antimatter mystery. The universe is made mostly of matter, but the known laws suggest that matter and antimatter should have been produced together in the early universe. If they had been created in exactly equal amounts and behaved too symmetrically, they would have annihilated, leaving behind a universe filled with radiation and very little of the material needed for stars, planets, oceans, or sleepy science videos. Something tipped the balance. Some process favoured matter by a tiny amount, and that tiny excess became everything we see. New particles could help explain that imbalance. They might have existed briefly in the early universe and decayed in ways that treated matter and antimatter differently. They may be gone now, too heavy or unstable to remain, but their influence could be written into the fact that matter survived. That is a remarkable possibility. The particles we are searching for may not all be present around us today. Some may be ancient actors whose work was done in the first moments of the cosmos. They may have shaped the conditions that allowed matter to remain, then vanished, leaving only consequences behind. Physics often works like this. Not every cause is still visible. A footprint in snow tells you someone walked there, even if they are no longer standing in the garden. The matter in your hand may be the footprint of processes involving particles that disappeared almost as soon as the universe began. Particles beyond the standard model might also reveal whether the forces of nature are connected more deeply than they appear. The electromagnetic force, the weak nuclear force, and the strong nuclear force behave differently in the world we know. But there are hints that at extremely high energies, such as those in the early universe, the forces may have been more unified. A new particle could be a sign of such unification. It might belong to a larger framework where quarks and leptons are related, where forces that now seem separate were once part of a single structure. If this is true, then the differences we observe today could be the cooled, separated remains of an earlier unity. The universe would be like a frozen landscape where once there was a single flowing sea, and the particles we know are the ice patterns left behind. This is one reason physicists search for rare processes such as proton decay. If protons are not perfectly stable, if they can transform through extremely rare events, it would suggest that matter particles are connected in ways the Standard Model does not allow. No proton decay has been confirmed, and if it happens, it must be incredibly rare. But the search continues because the meaning would be enormous. A single confirmed event would tell us that the apparent stability of ordinary matter is not absolute. The atoms around us would still be stable for all practical purposes, of course. Your table would not suddenly dissolve during breakfast. But at a deep level, matter would be part of a larger story of transformation. New particles might also show us how the Higgs field fits into the larger structure of nature. The Higgs boson was a triumph, but it did not answer every question about mass. It confirmed that the Higgs field is real in the sense required by the Standard Model, but why the Higgs has its particular properties remains mysterious. Supersymmetric particles, composite Higgs structures, hidden sector particles, or other new physics could reveal whether the Higgs is truly fundamental or part of something deeper. The Higgs may be a doorway, not a final brick. It may connect ordinary particles to hidden fields. It may have shaped the early universe in ways we do not yet understand. It may even relate to dark matter through what physicists call a portal, a small connection between our known particle world and a hidden one. A hidden sector would be especially fascinating. Imagine that the Standard Model is not the entire particle universe, but one sector, one family of fields and interactions that happens to include light, atoms, chemistry, and us. Somewhere alongside it, not in a separate place exactly, but in the same universe with only faint connections, there could be other particles governed by their own forces. They might not feel electromagnetism. They might not interact with ordinary matter except through gravity or tiny portals. They could be simple, with only one or two particles, or more complex, with dark forces and dark interactions. We should be careful not to turn this into fantasy too quickly. A hidden sector does not mean a shadow version of Earth or dark trees and dark teapots drifting invisibly through the room. But it could mean that nature has more fields and particles than the ones that build the visible world. If such a hidden sector exists, it would change our sense of what the word universe means. We often think of the universe as what can be seen, or at least what can be detected through light. But physics has already taught us that light is only one messenger. Gravity tells us things light cannot. Neutrinos tell us things light cannot. Gravitational waves tell us things light cannot. Hidden particles would extend that lesson further. Reality may contain layers that are not dark because they are far away, but because they do not speak the language of light. They may be present everywhere, but nearly silent to our instruments. Particles beyond the Standard Model might also help bring gravity into the quantum world. This is one of the deepest unfinished problems in physics. The Standard Model describes particles and forces using quantum field theory. General relativity describes gravity as the curvature of space and time. Both work beautifully in their own domains, but they do not yet form one complete picture. A particle such as the graviton is often imagined as the quantum carrier of gravity, though detecting it directly may be far beyond practical reach. Still, clues from particle physics could point toward a deeper theory, where gravity and quantum mechanics are part of the same framework. Supersymmetry, extra dimensions, string theory, and other approaches all try in different ways to close the gap. A new particle could be a signpost on that road. Extra dimensions are another possibility that has appeared in theories beyond the Standard Model. These are not dimensions in the loose science fiction sense, where one steps through a glowing doorway into a parallel castle. In physics, extra dimensions would mean additional directions or structures beyond the familiar 3 dimensions of space, perhaps curled up or hidden at extremely small scales. If they exist, they could affect particle behavior or produce new particles that appear as heavier copies of known ones. Colliders might detect signs of such effects, or precision experiments might reveal deviations from expected behaviour. So far, no confirmed evidence has appeared. But the idea shows how new particles might not only add ingredients, but also reveal hidden geometry in reality itself. Another thing new particles might reveal is why the standard model has its particular pattern of generations. The known matter particles come in repeated families. The first family builds ordinary matter. The second and third contain heavier relatives that appear briefly in high-energy processes and then decay. Why 3? Why these masses? Why these mixing patterns? The standard model describes the pattern but does not explain it fully. New particles or symmetries might show that the generations are part of a deeper structure. Perhaps they arise from hidden geometry, from flavor symmetries, from interactions with unknown fields, or from something not yet imagined clearly. This is one of those mysteries that feels less famous than dark matter, but just as revealing. Nature repeated herself 3 times, and we do not know why. There is a larger philosophical point here too. New particles might reveal that what we call fundamental is temporary. In the 19th century, atoms were sometimes treated as the smallest pieces of matter. Then electrons and nuclei were discovered. Then protons and neutrons were understood. Then quarks appeared. The boundary of fundamental matter moved downward again and again. Today, quarks, leptons, gauge bosons, and the Higgs boson are treated as fundamental in the standard model. They may truly be fundamental, or they may be the current visible layer. If new particles are found, especially if they point to compositeness or deeper structure, our idea of the smallest ingredients may shift again. The universe has done this before. It is under no obligation to stop now. But perhaps the most important thing particles beyond the standard model might reveal is not a single answer, but a new kind of question. When the electron was discovered, it did not merely add one particle. It opened the world of atomic structure and electronics. When the nucleus was discovered, it opened nuclear physics. When antimatter was predicted and found, it changed our understanding of symmetry and the possible forms of matter. When neutrinos were confirmed, they opened a nearly invisible channel of information from the sun and the stars. When the Higgs boson was discovered, it confirmed a field that fills space and shapes the mass of particles. Each discovery did not close curiosity, it multiplied it. New particles beyond the standard model would likely do the same. This is why the search continues even after many experiments have found no confirmed new particles. The silence is not meaningless, but neither is it the end. The standard model remains successful, perhaps more successful than many expected. Every time it survives another precision test, it becomes more impressive. But the gaps remain. Dark matter remains unidentified. Neutrino masses remain unexplained at a deep level. Matter-antimatter imbalance remains unresolved. Gravity remains outside the quantum particle framework. The Higgs still raises questions. The particle generations still look patterned but unexplained. These are not minor footnotes. They are large, persistent mysteries. It is possible that the next discovery will come from a collider. A new resonance might appear in collision data, a clean bump above background, announcing a heavy particle never seen before. It is possible the discovery will come from an underground detector, where a dark matter particle finally leaves the right kind of tiny signal. It could come from an axion experiment, where a hidden field converts into detectable light. It could come from neutrino experiments, where a sterile state or a matter-antimatter difference becomes undeniable. It could come from the sky, through gamma rays, cosmic rays, gravitational waves, or patterns in the large-scale structure of the universe. Or it could come from precision measurements, where a known particle behaves with the slightest but unmistakable disobedience. Discovery may also arrive slowly, not one dramatic announcement, but several clues from different directions that gradually form a picture. A small anomaly in one experiment, a compatible hint in another. a cosmological measurement that points the same way, a theoretical structure that begins to fit. This kind of discovery can be less cinematic but often more reliable. Nature may not care about dramatic timing. It may reveal itself like dawn, not lightning, with the shape of the landscape appearing little by little, and we should allow for surprise. The particle beyond the standard model that matters most may not be the one currently most popular. History is full of surprises. The muon was unexpected. The tau was unexpected. Neutrino oscillations were not part of the simplest old picture. The accelerating expansion of the universe was a shock. The universe often answers questions by changing the question. So while physicists propose axions, weakly interacting massive particles, sterile neutrinos, supersymmetric partners, dark photons, gravitons, and many other possibilities, the actual answer may bend around our expectations. That is not a reason to stop theorizing. It is a reason to keep experiments broad, careful, and honest. What would it feel like then to discover a particle beyond the standard model? At first, perhaps, it would feel technical. A plot, a signal, a statistical threshold, a conference room, a paper, teams checking and rechecking. Then gradually, the meaning would widen. Textbooks would change. The particle chart would grow. The early universe would be rewritten. Dark matter might gain an identity. The Higgs might gain a deeper context. Forces might appear more connected. Gravity might seem a little less isolated. The known world would remain the same in daily life. Tea would still cool. Alarms would still ring too early. Socks would still vanish with suspicious commitment. But underneath, the foundation would have shifted. The familiar world would be revealed as part of a larger one. There is comfort in knowing that science can hold uncertainty without turning it into emptiness. We do not know the particles beyond the standard model if they exist, but we know why we are looking. We know the clues, we know the gaps, we know the methods, we know the difference between a wish and evidence. That is the discipline of the search. It lets wonder remain wonder without becoming careless. It lets mystery stay alive while still asking for proof. So, as we come back from colliders, dark matter halos, neutrino beams, hidden sectors, and the early universe, we return to a simple thought. The standard model is a triumph, but perhaps not a final wall. It may be a window, polished by decades of experiment, through which we can see that reality continues beyond the frame. The particles we know build the visible world, but the invisible universe still pulls, shifts, and whispers. Somewhere beyond the known list may be the explanation for dark matter, the reason neutrinos are so light, the origin of matter's victory over antimatter, the deeper pattern behind the forces, or a clue to gravity's quantum nature. And maybe that is enough for tonight. Not a complete answer, but a clear place to rest the mind. The universe is known more deeply than ever before, and still it is not exhausted. Its smallest ingredients may not all have been named. Its quietest fields may not yet have been heard. Its darkest matter may still be waiting in the spaces between stars, passing through us gently, unnoticed, patient as night. So wherever you are listening from, whatever time it is around you, let the thought settle softly. We are made of particles the universe has already revealed, surrounded by mysteries it has not. And in that space between the known and the hidden, physics continues to listen.